Artificial intelligence refers to computer systems that are designed to simulate aspects of human intelligence. Traditionally, computer programs followed strict sets of rules defined by programmers. If a developer wanted a program to perform a task, they had to explicitly specify every instruction required to complete that task. Artificial intelligence takes a different approach. Instead of relying entirely on fixed rules, AI systems are designed to learn from data. These systems analyze large amounts of information, identify patterns, and use those patterns to make predictions or decisions. This ability to learn from data allows AI systems to improve their performance over time. There are several key capabilities that define modern AI systems. The first is learning. AI models are trained using large data sets, allowing them to recognize relationships and patterns within the data. For example, an AI model trained on thousands of images can learn to distinguish between different objects, such as cars, animals, or buildings. Another capability is pattern recognition. AI systems can detect patterns that may be difficult for humans to notice, especially when analyzing very large data sets. This makes AI extremely useful in fields such as finance, healthcare, and cybersecurity. Prediction is another important capability. AI models can analyze historical data and use that information to predict future outcomes. For example, an AI system might predict customer purchasing behavior or identify potential fraud in financial transactions. AI systems can also generate new content. This includes generating text, images, music, and even computer code. This capability is the foundation of what we now call generative AI. Finally, AI systems can automate complex decision-making processes. By analyzing multiple variables simultaneously, AI models can recommend actions or automatically make decisions in real time. These capabilities allow AI to be applied across a wide range of industries and use cases. From recommendation engines and fraud detection systems to voice assistants and autonomous vehicles, AI is becoming an essential technology across modern digital systems. Understanding these capabilities will help us better appreciate how AI solutions are designed and implemented. Modern AI systems typically operate across several core capability domains. These capabilities define how AI systems interact with data, interpret information, and produce useful outcomes. Understanding these capabilities helps us understand how AI powers many of the technologies we use every day. The first major capability of AI systems is perception. Perception refers to the ability of machines to interpret sensory data, such as images, video, and audio. For example, image recognition systems can identify objects in photos, while speech recognition systems can convert spoken language into text. These technologies are widely used in applications like facial recognition systems, voice assistants, and autonomous vehicles. The second capability is understanding. This involves processing and interpreting human language or complex information. Natural language processing, often abbreviated as NLP, allows AI systems to analyze text, determine sentiment, identify entities, and understand meaning within conversations or documents. Many chatbots and language translation systems rely on this capability. The third capability is decision-making. AI models can analyze patterns in historical data and use those patterns to support decision-making processes. For example, recommendation systems on streaming platforms suggest movies or shows based on previous viewing habits. predictive analytics systems help businesses forecast demand, manage supply chains, or detect potential risks. The fourth capability is content creation. This is one of the fastest growing areas of AI today. Generative models can create entirely new content based on patterns learned from training data. These systems can generate text, images, videos, music, and even software code. These four capabilities, perception, understanding, decision-making, and content creation, form the foundation of many modern AI applications. As AI technologies continue to evolve, these capabilities are becoming increasingly sophisticated. Systems are able to analyze larger datasets, understand more complex language structures, and generate more realistic content. By understanding these core capabilities, we can better understand how different AI technologies fit together and how organizations design intelligent systems to solve real-world problems. Machine learning is one of the most important subfields within artificial intelligence. While AI is a broad concept that refers to intelligent systems in general, machine learning focuses specifically on systems that learn patterns from data. Traditional software development relies heavily on explicit programming rules. Developers write code that defines exactly how a system should respond to different inputs. Machine learning takes a different approach. Instead of programming every rule manually, developers train models using data so that the system can learn patterns automatically. The machine learning process typically involves three main stages. The first stage is collecting and preparing data. Data is the foundation of any machine learning system. The quality and quantity of training data directly affect how well the model performs. The second stage is training the model. During training, algorithms analyze the dataset and identify relationships between different variables. The model gradually learns patterns within the data and adjusts its internal parameters to improve its predictions. The third stage is making predictions or performing inference. Once the model is trained, it can analyze new data and generate predictions based on what it learned during training. Machine learning is widely used across many industries. Email providers use machine learning to detect spam messages. Retail companies use recommendation systems to suggest products to customers. Financial institutions use machine learning to identify fraudulent transactions. Cloud platforms have significantly accelerated the adoption of machine learning by making powerful computing resources more accessible. On AWS, one of the key platforms used for machine learning development is Amazon SageMaker. This service allows developers to build, train, and deploy machine learning models at scale without managing the underlying infrastructure. Machine learning serves as the foundation for many advanced AI technologies, including deep learning and generative AI. Deep learning is a specialized subset of machine learning that focuses on neural networks with many layers. These neural networks are inspired by the structure of the human brain and are designed to process complex and high-dimensional data. While traditional machine learning models often rely on structured datasets and manually engineered features, deep learning models are capable of automatically learning hierarchical patterns from raw data. This makes deep learning particularly powerful for tasks involving images, audio, and natural language. Deep learning models use artificial neural networks composed of multiple layers. Each layer processes information and passes it to the next layer, gradually extracting more complex features from the data. For example, when analyzing images, early layers may detect simple edges or shapes, while deeper layers identify objects such as faces or vehicles. Deep learning has enabled major breakthroughs in several areas of AI. One of the most well-known applications is image recognition. Deep learning models can analyze medical images to detect diseases or identify objects in photographs with high accuracy. Another important application is speech processing. Voice assistants rely heavily on deep learning models to understand spoken language and convert it into text. Deep learning also plays a critical role in natural language understanding. Modern language models can analyze text, translate languages, summarize documents, and answer complex questions. However, deep learning models require significant computational resources. Training these models often involves processing massive datasets using powerful GPUs or specialized hardware. This is why cloud infrastructure plays such an important role in deep learning. Cloud platforms allow organizations to access high-performance computing resources on demand. Instead of investing in expensive hardware, companies can train and deploy deep learning models using scalable cloud services. Deep learning forms the technological foundation for many of the advanced AI systems we see today, including large language models and generative AI systems. Generative AI represents one of the most exciting and rapidly evolving areas of artificial intelligence. Unlike traditional AI systems that primarily analyze existing data and make predictions, generative AI systems are capable of creating entirely new content. This content can include text, images, audio, video, music, and even software code. Generative AI systems are powered by what are known as foundation models. These are very large neural networks trained on massive datasets that capture patterns across language, images, and other forms of data. Because of their scale and training approach, foundation models can perform many different tasks without being trained separately for each specific problem. For example, a single generative AI model might be able to write essays, summarize documents, translate languages, generate images, or assist with programming tasks. This flexibility is one of the main reasons generative AI has become so transformative across industries. Many modern AI tools and applications rely on generative AI models. Chatbots that answer questions, AI assistants that help with writing, and image generation tools that create artwork are all examples of generative AI in action. However, training and running foundation models requires enormous computing resources and specialized infrastructure. This is where cloud platforms play an important role. Cloud services allow organizations to access these powerful models without having to build the infrastructure themselves. Within the AWS ecosystem, developers can access foundation models through Amazon Bedrock. This service allows developers to integrate generative AI capabilities into their applications using APIs without needing to manage the underlying hardware or model training. By using services like Amazon Bedrock, organizations can build generative AI applications more quickly and securely while maintaining scalability. As generative AI continues to evolve, it is expected to play a major role in areas such as content creation, software development, customer service automation, and knowledge management. Understanding generative AI is essential for modern AI practitioners, which is why it is a key concept within the AWS AI Practitioner certification. At this point, it is important to clarify the relationship between artificial intelligence, machine learning, deep learning, and generative AI. These terms are often used interchangeably, but they actually represent different layers within the broader AI ecosystem. Artificial intelligence is the broadest category. It refers to any computer system that can perform tasks that normally require human intelligence. This includes reasoning, learning, perception, and decision-making. Within artificial intelligence, we find machine learning. Machine learning focuses specifically on systems that learn patterns from data rather than relying solely on explicitly programmed rules. Machine learning models improve their performance by analyzing data and identifying relationships between variables. Deep learning is a specialized subset of machine learning. Deep learning models use neural networks with many layers to analyze complex data sets such as images, audio signals, and natural language. Because of their ability to process large amounts of unstructured data, deep learning models have enabled major breakthroughs in areas like computer vision and speech recognition. Generative AI sits on top of deep learning technologies. These systems use large neural networks trained on massive datasets to generate new content rather than simply analyzing existing data. Generative AI models can create text, images, music, videos, and even software code. It can be helpful to visualize these technologies as a hierarchy. Artificial intelligence forms the outer layer. Within AI, we find machine learning. Within machine learning, we find deep learning. And within deep learning, we find generative AI models that specialize in content creation. Understanding this hierarchy is important because different AWS tools operate at different layers of the AI stack. Some services provide infrastructure for machine learning, while others provide direct access to advanced generative models. Recognizing where each technology fits helps practitioners choose the right tools when designing AI systems. Artificial intelligence is no longer limited to research labs or experimental projects. Today, AI technologies are widely adopted across nearly every major industry. In healthcare, AI systems are used to analyze medical images, detect diseases earlier, and assist doctors in diagnosing complex conditions. Machine learning models can identify patterns in medical data that might not be immediately visible to human experts. In finance, AI plays a critical role in fraud detection and risk management. Financial institutions use machine learning models to monitor transactions in real time and detect unusual behavior that may indicate fraudulent activity. Retail companies use AI to improve customer experiences. Recommendation systems suggest products based on customer behavior, while predictive analytics helps businesses forecast demand and manage inventory more efficiently. In manufacturing, AI systems enable predictive maintenance. Sensors installed in machinery generate large volumes of data that can be analyzed by machine learning models to predict when equipment may fail. This allows companies to perform maintenance before failures occur, reducing downtime and operational costs. Transportation and logistics companies also rely on AI for route optimization, demand forecasting, and fleet management. Across all these industries, the goal of AI adoption is to increase efficiency, reduce costs, and improve decision-making. One of the key reasons AI adoption has accelerated so quickly is the availability of cloud platforms. Cloud providers make powerful computing resources accessible to organizations of all sizes. This allows companies to experiment with AI solutions without needing to invest heavily in specialized infrastructure. As AI continues to mature, we can expect its influence to expand even further across industries. AWS provides a comprehensive ecosystem that supports the entire lifecycle of AI and machine learning development. Rather than offering just a single tool, AWS provides a full stack of services that allow organizations to build, train, deploy, and scale AI systems. At the foundation of this ecosystem is cloud infrastructure. AWS provides scalable computing resources, storage systems, and networking capabilities that enable organizations to process large data sets and train complex machine learning models. On top of this infrastructure sits the machine learning platform Amazon SageMaker. SageMaker allows developers and data scientists to build, train, and deploy machine learning models without needing to manage the underlying infrastructure. It provides tools for data preparation, model training, experimentation, and deployment. For generative AI applications, AWS offers Amazon Bedrock. Bedrock provides access to powerful foundation models that can generate text, images, and other forms of content. Developers can integrate these models into applications using simple APIs. In addition to these platforms, AWS also provides pre-built AI services. These services allow developers to add advanced AI capabilities to applications without building machine learning models from scratch. Examples include services for computer vision, natural language processing, and speech recognition. Together, these layers form a powerful AI ecosystem that supports both beginners and advanced practitioners. By combining infrastructure, machine learning platforms, and pre-built AI services, AWS enables organizations to move from experimentation to production much more quickly. Understanding how these layers interact is important for designing scalable AI architectures. In this session, we explored the foundational concepts that underpin modern artificial intelligence and the tools used to build AI systems in the cloud. First, we defined artificial intelligence as the ability of computer systems to simulate aspects of human intelligence. AI systems can learn from data, recognize patterns, make predictions, generate content, and automate complex decision-making processes. We then explored the hierarchy of AI technologies. Machine learning is a subset of artificial intelligence that focuses on learning patterns from data. Deep learning is a specialized form of machine learning that uses multi-layer neural networks to analyze complex datasets. Generative AI builds on deep learning techniques to generate new content, such as text, images, and code. Next, we examined how AI technologies are transforming industries around the world. From healthcare and finance to retail and manufacturing, organizations are using AI to improve efficiency, reduce operational costs, and make better decisions. We also introduced the AWS AI ecosystem and the tools available to build AI applications in the cloud. AWS provides scalable infrastructure, machine learning platforms like SageMaker, and generative AI services like Bedrock. These tools allow organizations to develop AI systems without managing complex hardware or infrastructure. Understanding these foundational concepts is essential for anyone working with AI technologies or preparing for the AWS AI Practitioner certification exam. In the next lesson, we will take a deeper dive into generative AI and foundation models. We will explore how these models are trained, how they work internally, and how developers can integrate them into real-world applications. This knowledge will help you understand not only the technology behind modern AI systems, but also how to apply these tools effectively using the AWS platform. Generative AI works differently. Instead of only analyzing existing data, generative AI models learn patterns from extremely large datasets and then use those patterns to produce entirely new outputs. This is what makes them generative. The first step in this process is training. During training, a generative model is exposed to massive datasets containing text, images, code, or other types of information. These datasets can contain billions or even trillions of data points. By processing this data, the model learns patterns, structures, and relationships within the information. Once trained, the model can use what it has learned to generate new content that follows similar patterns. For example, a text generation model might learn grammar, vocabulary, and writing styles from the training data. When given a prompt, it can generate new sentences that follow those patterns. Because of this ability to recognize patterns and generate new outputs, generative AI models can perform a wide variety of tasks. They can write articles, summarize documents, translate languages, generate artwork, answer questions, and assist with coding tasks. Another important point is that generative AI systems typically rely on neural networks, particularly deep learning architectures such as transformers. These architectures allow models to process enormous amounts of information and generate complex outputs. Generative AI did not appear suddenly. It is the result of decades of progress in artificial intelligence research and computing technology. The next major development was machine learning. Machine learning allowed systems to learn patterns directly from data rather than relying on explicit rules. This made it possible to build models that could recognize patterns, make predictions, and improve over time. As machine learning evolved, researchers began developing deep learning models, which use neural networks with many layers. Deep learning made it possible to process complex data types such as images, audio, and natural language. This led to major breakthroughs in areas like speech recognition, computer vision, and language translation. Generative AI represents the next step in this evolution. Instead of focusing only on analyzing data, generative models are designed to create new outputs based on patterns learned during training. These technological advancements have made it possible to build extremely large neural networks capable of generating human-like text, realistic images, and complex software code. Today, generative AI is one of the fastest growing areas of artificial intelligence and is driving innovation across many industries. At the core of modern generative AI systems are foundation models. Foundation models are extremely large neural networks that are trained on massive datasets containing diverse information such as text, images, and code. For example, a single foundation model might be capable of performing tasks such as text generation, document summarization, language translation, question answering, and code generation. This flexibility makes foundation models incredibly powerful. One of the defining characteristics of foundation models is the scale of their training data. These models are often trained on trillions of tokens, which represent pieces of text or data from many different sources. The diversity of this training data allows the model to learn general patterns about language, reasoning, and knowledge. The diagram in the slide illustrates how one foundation model can support multiple tasks such as classification, summarization, translation, and question answering. Introduction to generative AI. Because foundation models require enormous computing resources to train, most organizations do not train these models themselves. Instead, they access them through cloud platforms and APIs. In the AWS ecosystem, developers can access foundation models through Amazon Bedrock. Amazon Bedrock is a fully managed service that provides access to multiple foundation models through a single API. This means developers can integrate powerful generative AI capabilities into their applications without needing to train or manage the underlying models. One of the major advantages of Amazon Bedrock is that it eliminates the need to manage complex infrastructure. Training and running large AI models requires powerful computing resources and specialized hardware. Bedrock handles all of this behind the scenes, so developers can focus on building applications. Another important benefit is security and scalability. Amazon Bedrock is designed to meet enterprise requirements for security, compliance, and reliability. Organizations can build generative AI solutions while maintaining control over their data and infrastructure. Using Bedrock, developers can build a wide variety of AI-powered applications. For example, they can create conversational assistants that answer questions, generate summaries of documents, automate customer support interactions, or assist with software development tasks. This allows companies of all sizes to build and deploy generative AI applications quickly and efficiently. In the next section, we will explore large language models, which are a specific type of foundation model designed to understand and generate human language. Large language models, often called LLMs, are a specialized type of foundation model designed specifically for understanding and generating human language. These models are trained on extremely large collections of text data gathered from sources such as books, websites, research papers, conversations, and code repositories. By analyzing these massive datasets, LLMs learn patterns in language, including grammar, sentence structure, context, and meaning. Unlike traditional NLP models that were designed to perform a single task, modern LLMs can perform many different tasks using the same underlying model. For example, An LLM can answer questions, summarize long documents, translate text between languages, generate articles, or assist with writing computer code. One of the reasons LLMs are so powerful is the scale of their training data. Modern models are trained on billions or even trillions of tokens. This scale allows the model to develop a broad understanding of language and general knowledge. Many AI assistants, chatbots, and coding tools rely on LLM technology. These models power systems that can answer complex questions, provide explanations, generate summaries, and even assist developers by writing code. However, it is important to remember that LLMs do not truly understand language the way humans do. Instead, they rely on statistical patterns learned from training data. They predict the most likely next token based on probability distributions derived from that training data. Despite this limitation, LLMs have become one of the most important components of modern generative AI systems. Their ability to process natural language makes them extremely valuable for applications such as customer support automation, document analysis, research assistance, and knowledge management. To understand how large language models process text, we need to understand the concept of tokens. Language models do not read full words or sentences the way humans do. Instead, they process text as smaller pieces of information called tokens. Tokenization is an important step because it allows language models to handle text in a structured way. By breaking language into tokens, models can analyze patterns in how words and phrases appear together. Another important concept is the context window. The context window refers to the maximum number of tokens that a model can process at one time. In simple terms, it defines how much information the model can remember during a conversation or while analyzing a document. For example, if a model has a small context window, it may forget earlier parts of a conversation. But with a larger context window, the model can maintain context across multiple messages, resulting in more consistent and accurate outputs. Understanding tokens and context windows is important because these concepts directly influence how generative AI systems process information and generate responses. Another fundamental concept in modern AI systems is embeddings. Embeddings are numerical representations of data that allow machines to understand relationships and meaning within information. When humans read text, we understand meaning through context and experience. Computers, however, cannot directly interpret words or concepts. To enable machines to process language, AI systems convert words, sentences, or documents into mathematical vectors called embeddings. These vectors capture semantic relationships between pieces of information. For example, words with similar meanings will have similar embedding vectors. This allows AI systems to measure similarity between texts based on meaning rather than exact keywords. Embeddings enable several powerful capabilities. One of the most important is semantic search. Instead of searching for exact keyword matches, semantic search allows systems to retrieve information that is conceptually related to a query. Embeddings also power recommendation systems. For example, streaming platforms can recommend movies or songs that are similar to content a user previously enjoyed. Embeddings are also a key component of modern generative AI architectures, such as retrieval augmented generation, often called RAG. In these systems, embeddings are used to retrieve relevant information from a knowledge base before generating a response. By converting meaning into numbers, embeddings allow AI systems to perform complex reasoning and similarity analysis across large datasets. Embeddings play a critical role in many modern AI applications. One of the most common uses is semantic search. Traditional search engines rely heavily on keyword matching. This means they return results that contain the exact words used in a query. However, semantic search uses embeddings to understand the meaning of the query. For example, if a user searches for ways to reduce business costs, a semantic search system might return documents related to improving operational efficiency or optimizing expenses, even if the exact keywords are different. This makes search results much more accurate and useful. Embeddings also power recommendation systems. These systems analyze similarities between users, products, or content. For example, online retailers use embeddings to recommend products that are conceptually similar to items a customer previously viewed or purchased. Another important application is chatbots and knowledge assistants. Embeddings allow these systems to retrieve relevant information from large knowledge bases. When a user asks a question, the system converts the query into an embedding and searches for documents with similar embeddings. This approach is commonly used in retrieval augmented generation systems. In RAG systems, embeddings help retrieve relevant documents, and generative models use that information to produce more accurate responses. Generative AI is rapidly transforming how organizations operate across many industries. One of the most visible use cases is content creation. Businesses use generative AI to write blog posts, marketing copy, product descriptions, and social media content. This allows companies to produce large amounts of content quickly while maintaining consistency. Another major use case is software development. Generative AI tools can assist developers by generating code snippets, identifying bugs, and suggesting improvements. These tools help developers work more efficiently and accelerate the software development process. Customer support is another area where generative AI is having a significant impact. AI-powered chatbots can answer common customer questions, resolve issues, and provide support around the clock. This improves response times and reduces the workload on human support teams. Generative AI also plays an important role in knowledge management. Organizations often have large collections of documents, reports, and internal knowledge. Generative AI systems can summarize documents, extract key insights, and retrieve relevant information when employees need it. Beyond these applications, generative AI is being used in fields such as education, healthcare, entertainment, and scientific research. As the technology continues to evolve, new use cases are emerging across nearly every industry. In the next lesson, we will explore prompt engineering, which focuses on how to interact with generative AI systems effectively in order to produce high-quality outputs. To understand how large language models process text, we need to examine a fundamental concept called tokens. Unlike humans, language models do not read sentences word by word. Instead, they process text by breaking it into smaller units called tokens. A token can represent an entire word, part of a word, punctuation, or even a special symbol. For example, the sentence "AI is powerful" may be split into tokens such as AI, is, power, and full. Once text is converted into tokens, each token is transformed into a numerical representation that the model can process mathematically. This process is called tokenization, and it is the first step in how large language models interpret language. Because neural networks operate on numbers rather than raw text, tokens allow the model to convert language into a format that can be analyzed by the model. Tokens are also important for determining how much information a model can process at once. Every time you send a prompt to an AI model, that prompt is converted into tokens. The model then analyzes the tokens to determine the most likely next token in the sequence. By repeatedly predicting the next token, the model generates full sentences and paragraphs. This token-based approach allows language models to process a wide variety of text inputs, from short questions to long documents. However, there are limits to how many tokens a model can handle at once, which leads us to the next concept: context windows. The context window is another key concept in understanding how large language models work. The context window refers to the maximum number of tokens a model can process in a single interaction. In simple terms, the context window determines how much information the model can remember while generating a response. When you provide a prompt to an AI model, the model analyzes the tokens within that prompt. If the prompt becomes too long and exceeds the context window limit, the model cannot process the entire input. For example, if a model has a small context window, it may only be able to process short questions or short conversations. If a conversation becomes too long, the model may lose track of earlier parts of the dialogue. Models with larger context windows can process longer documents and maintain longer conversations. This allows them to analyze more complex inputs and generate more coherent responses. As shown in the slide, smaller context windows often result in fragmented responses or limited document analysis. Larger context windows allow models to analyze entire documents, maintain multi-turn conversations, and generate richer responses. Understanding context windows is important when designing AI applications because it affects how much information the model can use when generating responses. Another essential component of modern AI systems is embeddings. Embeddings are numerical representations of data that allow machines to understand relationships between pieces of information. Humans interpret meaning through language and context. However, computers operate using numbers. To enable machines to understand meaning, text or images must be converted into mathematical representations. Embeddings transform words, sentences, or documents into vectors, essentially lists of numbers, that capture semantic meaning. Words or phrases with similar meanings will have embedding vectors that are close to each other in mathematical space. For example, the words car and automobile would have embeddings that are very similar because they represent the same concept. Similarly, words like king and queen may share similar relationships in embedding space. This ability to represent meaning numerically allows AI systems to perform powerful tasks such as measuring similarity between texts. Instead of relying on exact keyword matches, systems can compare embeddings to determine how conceptually similar two pieces of information are. Embeddings are widely used in search engines, recommendation systems, and conversational AI systems. They also serve as a key building block in many generative AI architectures. By converting meaning into numbers, embeddings allow AI models to process language, understand relationships, and retrieve relevant information. Embeddings are used in many modern AI applications because they allow systems to understand semantic relationships between pieces of data. One important application is semantic search. Traditional search engines rely on keyword matching. This means they return results that contain the same words used in the search query. However, semantic search uses embeddings to understand the meaning of the query. For example, if someone searches for ways to improve business efficiency, a semantic search system might return results about reducing operational costs or optimizing workflows, even if the exact words are different. Embeddings also power recommendation systems. These systems analyze similarities between users, products, or content. For example, online retailers use embeddings to recommend products that are conceptually similar to items a customer previously viewed. Another major application is document clustering. Organizations often have thousands of documents that need to be organized. Embeddings allow AI systems to group similar documents together automatically. This process is a key part of retrieval augmented generation, or RAG systems, where relevant documents are retrieved before the AI generates a response. Because of these capabilities, embeddings play a critical role in enabling modern AI applications. Generative AI is transforming how organizations operate across many industries. One of the most visible applications is content creation. Businesses use generative AI tools to create blog posts, marketing materials, product descriptions, and social media content. Customer support is another area where generative AI is having a major impact. AI-powered chatbots can answer common customer questions, resolve issues, and provide assistance 24 hours a day. Generative AI is also widely used in knowledge management. Many organizations store large amounts of internal documentation and reports. Generative AI systems can summarize documents, extract key insights, and retrieve relevant information when employees need it. Beyond these examples, generative AI is being used in education, healthcare, media production, and scientific research. As the technology continues to evolve, new applications are emerging that enable organizations to automate workflows and unlock new forms of creativity. The impact of generative AI extends across nearly every major industry. Businesses are rapidly adopting generative AI technologies to improve efficiency, automate tasks, and enhance decision-making. In software development, AI coding assistants help developers write and debug code more efficiently. These tools reduce development time and improve productivity. Customer service organizations use AI chatbots to provide instant support and resolve customer issues without requiring human intervention. This allows companies to deliver faster service while reducing operational costs. Generative AI also plays a growing role in knowledge management. Organizations often struggle to manage large collections of documents and internal knowledge. AI systems can analyze these documents, summarize key insights, and help employees find relevant information quickly. Across industries, generative AI is enabling new forms of automation and innovation. Companies that adopt these technologies early can gain significant competitive advantages. In this lesson, we explored the fundamental concepts that power modern generative AI systems. First, we learned that generative AI differs from traditional AI because it focuses on creating new content rather than simply analyzing existing data. These systems can generate text, images, video, music, and software code. Next, we explored large language models, which specialize in understanding and generating human language. These models power many modern AI assistants and conversational systems. We also discussed tokens and context windows, which determine how models process language and how much information they can analyze at one time. Another important concept we covered was embeddings, which convert meaning into numerical vectors. Embeddings allow AI systems to measure similarity between pieces of information and enable technologies like semantic search and recommendation systems. Finally, we explored real-world use cases for generative AI across industries such as content creation, software development, customer support, and knowledge management. Understanding these concepts provides a strong foundation for building and using generative AI systems. In the next lesson, we will explore prompt engineering, which focuses on how to interact effectively with generative AI models to produce accurate and useful outputs. Foundation models are defined as large AI models trained on massive and diverse datasets and then adapted for many downstream tasks. Instead of focusing on a single task, these models learn general patterns that allow them to support multiple types of applications. One of the defining characteristics of foundation models is their broad training process. These models are trained on extremely large datasets that may include text, images, audio, code, and other forms of information. By analyzing such large volumes of data, the model learns relationships between concepts, patterns in language, and structures within images or other data types. Because of this broad training, foundation models are multitask capable. A single model can perform tasks such as summarization, translation, question answering, content generation, and even image creation. This makes them far more flexible than traditional machine learning models. Another important aspect of foundation models is that they act as a base layer for generative AI applications. Developers can build applications on top of these models rather than training their own models from scratch. For example, a developer building a customer service chatbot could use a foundation model to understand questions and generate responses. Similarly, a company building a document summarization tool could rely on a foundation model's language capabilities. Foundation models are also adaptable. They can be customized using techniques such as prompting or fine-tuning. Prompting involves giving the model instructions through natural language inputs, while fine-tuning involves additional training using specialized datasets. Because foundation models require enormous computing resources to train, most organizations do not build them independently. Instead, they access them through cloud services or APIs. Understanding how foundation models work helps explain why generative AI has advanced so quickly in recent years. The development and deployment of foundation models involves a complex ecosystem of organizations and technologies. This ecosystem includes several layers that work together to deliver AI capabilities from research laboratories to end users. The first layer of this ecosystem consists of model providers. These organizations design and train large AI models using massive datasets and specialized computing infrastructure. Training these models requires enormous resources, including powerful GPUs, advanced algorithms, and large engineering teams. The second layer is cloud platforms. Cloud providers host these models and provide access to them through APIs or managed services. This allows developers to integrate AI capabilities into their applications without needing to train or host models themselves. The third layer includes application developers. These developers build AI-powered products by integrating foundation models into applications. Examples include chatbots, document analysis tools, recommendation systems, and AI assistants. The final layer consists of end users who interact with AI systems through applications, websites, or software tools. This ecosystem enables innovation across many industries. Researchers develop new model architectures. Cloud providers deliver scalable infrastructure. Developers create applications, and users benefit from AI-powered capabilities. By understanding this ecosystem, we can see how foundation models move from research labs to real-world products. Foundation models are developed by a variety of organizations across the technology industry. These providers generally fall into several categories, each playing a unique role in advancing AI technology. The first category includes AI research laboratories. These organizations focus on pushing the boundaries of AI research and developing new model architectures. Many early breakthroughs in generative AI originated from research institutions and specialized AI labs. The second category includes large technology companies, sometimes called hyperscalers. These organizations have the computing infrastructure and financial resources required to train extremely large models. They often develop proprietary models that power their own AI services and products. The third category includes cloud providers. Cloud platforms host foundation models and make them available through APIs and managed services. This approach allows developers to use powerful AI models without needing to train them independently. Different model providers often specialize in different types of models. Some focus primarily on language models, while others develop image generation models, multimodal systems that process multiple data types, or speech recognition models. By offering models through APIs or cloud platforms, these providers allow developers to integrate advanced AI capabilities into applications with relatively little effort. This model provider ecosystem has accelerated the adoption of generative AI across industries. Within the AWS ecosystem, developers can access foundation models using a managed service called Amazon Bedrock. This service provides a centralized platform where developers can access multiple foundation models through a single API. One of the major benefits of Amazon Bedrock is that it eliminates the need for developers to manage complex AI infrastructure. Training and running large models requires powerful hardware and specialized engineering expertise. Bedrock abstracts this complexity so developers can focus on building applications rather than managing servers. Another advantage is multi-model access. Developers can choose from several foundation models provided by different model developers. This flexibility allows organizations to experiment with different models and select the one that best fits their needs. Security and compliance are also important features of the AWS environment. The platform integrates with identity management, encryption systems, and secure networking tools. This allows enterprises to build generative AI applications while maintaining strict security controls. The platform is also designed to scale automatically. As application demand grows, the underlying infrastructure expands to handle increased workloads. Because of these capabilities, Amazon Bedrock has become an important platform for organizations that want to build generative AI applications without managing the underlying model infrastructure. In the next section, we will explore the differences between open models and closed models, which is another key concept when selecting foundation models for enterprise AI applications. In this section, we will explore an important concept in the foundation model ecosystem: the difference between open models and closed models. Foundation models today fall into two major categories depending on how they are distributed and controlled. Open models are publicly available models whose weights can often be downloaded and run locally or on private infrastructure. Developers can modify them, fine-tune them, and deploy them inside their own environments. Because of this flexibility, open models are widely used by researchers, startups, and organizations that want maximum control over their AI systems. On the other hand, closed models are controlled by the organizations that build them. These models are typically accessed through APIs rather than downloaded directly. The model provider manages the infrastructure, updates the models, and controls access. Each approach has advantages and trade-offs. Open models provide flexibility and customization, while closed models often provide higher reliability and performance. In enterprise environments, organizations rarely choose only one approach. Instead, many AI architectures combine both types of models. For example, a company may use closed models for production workloads where reliability and performance are critical. At the same time, they may use open models internally for experimentation, research, or specialized tasks. Choosing between open and closed models depends on several factors, including infrastructure capabilities, security requirements, compliance constraints, and cost considerations. Understanding this distinction is important because it directly influences how AI systems are built, deployed, and managed in real-world applications. Open models provide several important advantages for organizations and developers who want flexibility when building AI systems. One of the biggest advantages is deep customization. Because open models provide access to model weights and architectures, developers can fine-tune them using proprietary datasets. This allows organizations to create models that are tailored to their specific use cases. For example, a healthcare company might fine-tune a language model using medical documentation so that it better understands medical terminology. Similarly, a financial institution might customize a model to better analyze financial reports or regulatory documents. Another advantage of open models is transparency. Developers can inspect how the model works, including its architecture and training processes. This level of transparency is valuable for organizations that require greater control or regulatory oversight. Open models also provide deployment flexibility. They can be run on private infrastructure, inside secure environments, or within a company's own cloud environment. This can be especially important for organizations dealing with sensitive or confidential data. Another potential benefit is cost control. When models are deployed on internal infrastructure, organizations may avoid per-request API costs that are often associated with closed model services. However, open models also require organizations to manage infrastructure, scaling, updates, and security. This means that while they offer flexibility, they also require more operational responsibility. For organizations with strong engineering capabilities, open models can be a powerful option for building specialized AI systems. Closed models provide a different set of benefits, particularly for organizations that want to deploy AI solutions quickly and reliably. One of the most significant advantages is performance. Closed models are often trained on extremely large datasets using proprietary techniques. These training processes require massive computing resources that only large technology companies typically possess. As a result, closed models often achieve very high performance across a wide range of tasks. Another advantage is ease of integration. Closed models are typically accessed through APIs, which means developers can integrate powerful AI capabilities into applications with just a few lines of code. There is no need to train models or manage complex infrastructure. Closed models also provide enterprise reliability. Model providers manage scaling, uptime, and infrastructure maintenance. This allows organizations to focus on building applications rather than managing AI systems. Security and compliance are also important benefits. Many closed model providers offer enterprise-grade security features, such as encryption, identity management, and compliance certifications. Another advantage is operational simplicity. Because the model provider manages the underlying infrastructure, organizations do not need specialized machine learning infrastructure teams to deploy and maintain models. For many companies, especially those just beginning their AI journey, closed models offer a fast and reliable way to adopt generative AI technologies. Selecting the right foundation model is an important decision when building AI applications. Different models have different strengths, costs, and operational requirements. One of the first considerations in model selection is task fit. Different models are designed for different types of tasks. Some models specialize in text generation, while others focus on image generation, speech processing, or multimodal tasks that combine several data types. Another important factor is latency, which refers to how quickly the model produces responses. Some applications require real-time responses, such as chat assistants or customer service bots. Other applications, such as batch document analysis, may tolerate longer processing times. Cost is another key consideration. Organizations must evaluate the total cost of using a model. This includes API usage fees, infrastructure costs, and potential scaling costs as usage grows. Security and compliance are also critical in enterprise environments. Organizations handling sensitive data must ensure that their chosen model meets security standards and regulatory requirements. A practical approach to model selection is to test several candidate models using real production data. Benchmarking models against real tasks often provides better insights than relying only on public benchmarks. Choosing the right model requires balancing performance, cost, security, and operational complexity. Before deploying a foundation model into production, organizations must carefully evaluate its performance across several key dimensions. The first dimension is quality. This refers to how accurate and useful the model's outputs are. For example, does the model produce correct answers, relevant summaries, or useful generated content? The second dimension is speed. In many applications, response time is critical. Evaluating speed involves measuring how quickly the model begins generating output and how many tokens it can generate per second. The third dimension is scalability. Organizations must determine whether the model can handle large workloads. This includes testing how well the system performs when many users interact with it simultaneously. The fourth dimension is reliability. AI systems must produce consistent results over time. Organizations evaluate error rates, system stability, and how well the model handles unexpected inputs. These four dimensions, quality, speed, scalability, and reliability, help organizations determine whether a model is ready for production deployment. By carefully evaluating models across these criteria, organizations can ensure that their AI systems deliver reliable and high-quality performance in real-world applications. In this lesson, we explored the role of foundation models and model providers in the modern AI ecosystem. These models have become the foundational infrastructure behind many of the generative AI applications we see today. The first key takeaway is that foundation models act as the core layer of modern AI systems. Instead of training separate models for each individual task, organizations can rely on large models that have already been trained on massive datasets. These models can then be adapted for many different applications, such as text generation, summarization, translation, image creation, and knowledge retrieval. This approach dramatically accelerates the development of AI-powered products. Another important concept we discussed is the distinction between open models and closed models. Open models provide flexibility and transparency because developers can download, modify, and deploy them on their own infrastructure. This allows organizations to customize models using their own proprietary datasets. However, open models often require additional operational effort because organizations must manage infrastructure, scaling, and security themselves. Closed models, on the other hand, are typically accessed through APIs and managed by the model provider. These models often offer higher performance, enterprise reliability, and simpler integration because the provider manages the underlying infrastructure. For many organizations, closed models provide the fastest path to deploying AI-powered applications. We also examined model selection strategies. Choosing the right model depends on several factors including task requirements, latency, cost, security considerations, and compliance requirements. There is no single model that is best for every use case. Instead, organizations should evaluate several candidate models and test them against real-world workloads. Another key idea is model evaluation. Before deploying AI systems into production environments, organizations should evaluate models across four important dimensions: output quality, speed of response, scalability under load, and long-term reliability. These evaluations help ensure that AI systems perform consistently and meet operational requirements. Overall, foundation models are transforming how software systems are built. Instead of writing complex logic for every task, developers can leverage powerful models that understand language, images, and knowledge. In the next lesson, we will move into prompt engineering, where we will learn how to interact effectively with foundation models to produce accurate, reliable, and high-quality outputs. To understand prompt engineering, we must first understand how prompts influence AI behavior. When a generative AI model receives a prompt, it analyzes the text and uses it as context to determine what type of response should be generated. A prompt can contain several different elements. It may include a question, a direct instruction, background information, formatting requirements, or examples of the desired output. Each of these elements helps guide the model toward producing a more accurate response. For example, a simple prompt might ask a model to summarize an article. However, if the prompt includes additional instructions, such as limiting the summary to 3 bullet points or writing in a professional tone, the model will adjust its output accordingly. The prompt therefore serves as both instruction and context for the AI system. The model does not independently decide what the user wants. Instead, it interprets the prompt and attempts to generate the most appropriate response based on that input. Because of this, the structure and clarity of the prompt directly influence several aspects of the AI's response. These include output accuracy, reasoning ability, formatting, and overall reliability. For example, vague prompts may lead to incomplete or inconsistent answers. In contrast, well-designed prompts provide clear instructions and constraints that guide the model toward producing higher quality outputs. Another important point is that generative AI models do not truly understand instructions in the same way humans do. Instead, they rely on patterns learned during training. The prompt helps activate the relevant patterns that the model uses to generate its response. By carefully designing prompts, users can influence how the model interprets the task and how it structures its response. This is why prompt engineering is such a powerful technique. A well-crafted prompt can significantly improve the performance of AI systems without requiring any changes to the model itself. There are several types of prompts that can be used when interacting with generative AI systems. Each type serves a different purpose depending on the task being performed. One common type is the instruction prompt. Instruction prompts directly tell the model what task to perform. For example, a prompt might say, "Summarize the following article," or "Explain the concept of machine learning." These prompts are straightforward and work well for tasks where the objective is clearly defined. Another type is the question prompt. In this case, the user asks the model a specific question. For example, a user might ask, "What are the benefits of cloud computing?" The model then generates a response based on the information it has learned during training. A third type is the contextual prompt. Contextual prompts provide background information that helps guide the model's response. For example, a prompt might include a paragraph of text followed by a question about that paragraph. The context helps the model produce a more relevant answer. Each of these prompt types helps shape how the AI system interprets the task. Instruction prompts focus on actions, question prompts focus on answers, and contextual prompts provide additional guidance. Choosing the right type of prompt is an important part of prompt engineering. Different tasks may require different prompt styles. For example, summarization tasks often use instruction prompts, while research questions may rely on question prompts. By understanding these different prompt types, users can design prompts that better match the specific task they want the AI system to perform. Prompt patterns are structured templates that help guide AI systems toward producing clearer and more reliable outputs. Instead of writing prompts randomly, prompt patterns provide repeatable structures that consistently generate better results. One example of a prompt pattern is role prompting. In this approach, the model is asked to act as a specific type of expert. For example, a prompt might say, "Act as a financial analyst and evaluate this report." This helps guide the model to generate responses that match the expertise of that role. Another common pattern is step-by-step instructions. This pattern asks the model to explain a process in a sequence of steps. For example, a prompt might say, "Explain the process step by step." This encourages the model to organize its response more clearly. A third pattern is structured output prompting. In this pattern, the prompt specifies the format in which the response should be generated. For example, the prompt might request bullet points, tables, or structured data, such as JSON. Prompt patterns help reduce ambiguity and improve output quality. By clearly defining the role, structure, and expectations of the response, these patterns help the model generate more useful and consistent answers. In many enterprise applications, prompt patterns are standardized and reused across different systems. This ensures consistent AI behavior across applications. Understanding and applying prompt patterns is one of the most effective ways to improve the reliability of generative AI systems. One of the most effective prompt patterns is role-based prompting. In role-based prompting, the prompt instructs the model to behave as a specific type of expert or professional. For example, a prompt might say, "Act as a cybersecurity expert and explain how phishing attacks work." By assigning a role to the model, the prompt helps guide the style, tone, and depth of the response. Role-based prompting works because large language models have been trained on vast amounts of information across many fields. When the model is asked to assume a particular role, it activates patterns associated with that domain. This technique often produces more structured and professional responses. For example, asking a model to act as a teacher may produce a more educational explanation, while asking it to act as a consultant may produce a more analytical response. Role-based prompting also improves domain-specific depth. When the model assumes a role, it tends to generate explanations that are more aligned with the expertise associated with that role. Another benefit is improved clarity. Responses generated through role-based prompts are often more organized and easier to understand. Because of these advantages, role-based prompting is widely used in many AI applications, including customer support systems, virtual assistants, training tools, and enterprise knowledge systems. By combining role-based prompts with other prompt patterns, developers can design AI interactions that produce more reliable and useful results. Another important concept in prompt engineering is the use of system prompts. System prompts define the overall behavior, tone, and rules that guide how an AI assistant responds throughout a conversation. Unlike regular prompts that represent a user's question or request, system prompts are typically defined at the beginning of an interaction. They act as a set of instructions that shape the assistant's behavior before any user message is processed. For example, a system prompt might say, "You are a helpful AI assistant that explains technical concepts in simple language for beginners." This instruction influences how the model responds to every question that follows. The model will attempt to generate explanations that are clear, simple, and accessible to someone who may not have a technical background. System prompts are widely used in applications such as chatbots, virtual assistants, and enterprise AI tools. They help ensure that the AI behaves consistently across multiple conversations and users. A well-designed system prompt typically includes several components. These may include tone instructions, which determine whether the assistant should respond formally, casually, or conversationally. Another component is formatting rules, which may specify how answers should be structured, such as using bullet points or short explanations. System prompts can also include safety guidelines. These instructions help ensure that the AI avoids generating harmful or inappropriate content and stays within acceptable boundaries. Another important element is behavior constraints. These instructions may define how the AI should respond to certain types of questions or when it should refuse to answer. By carefully designing system prompts, developers can control the behavior of AI systems and ensure consistent interactions across applications. Few-shot prompting is a powerful technique used to improve the performance of generative AI models by providing examples of the desired output. Instead of simply telling the model what to do, few-shot prompting shows the model a few examples of how the task should be performed. These examples help the model understand the pattern it should follow when generating its response. For example, imagine we want a model to translate English phrases into Spanish. A basic instruction might say, "Translate English to Spanish." However, this instruction alone may not always produce consistent results. With few-shot prompting, we provide examples such as hello, hola, good morning, buenos dias. Then we ask the model to complete a new example, such as thank you. Because the model has already seen examples of the correct format and pattern, it can more easily produce the correct answer. Few-shot prompting works because it helps the model recognize the structure of the task. The examples act as a guide that demonstrates the expected relationship between input and output. This technique is particularly useful when working with tasks that require consistent formatting, classification, or structured responses. Few-shot prompting can significantly improve model performance without requiring any additional training. By simply adding a few examples to the prompt, users can guide the model toward more accurate outputs. Because of its effectiveness, few-shot prompting is widely used in many AI applications, including text classification, translation systems, and automated data processing tools. Another important prompt engineering technique is chain-of-thought prompting. This technique encourages the model to show its reasoning process step by step, rather than simply providing a final answer. When solving complex problems, humans often work through intermediate steps before reaching a conclusion. Chain-of-thought prompting applies this same principle to AI models. For example, instead of asking a model, "What is 27 multiplied by 14?" we might ask, "Explain the steps needed to calculate 27 multiplied by 14." By asking the model to explain its reasoning, we encourage it to break the problem into smaller steps. This often improves accuracy, especially for tasks that involve logical reasoning or calculations. Chain-of-thought prompting is particularly useful for problems that require multi-step reasoning. Examples include mathematical calculations, logical puzzles, analytical questions, and complex decision-making tasks. When the model explains its reasoning step by step, it reduces the likelihood of making simple mistakes. This approach also makes the output easier to understand and verify. Another advantage is that chain-of-thought reasoning can reveal how the model arrived at its conclusion. This transparency can be helpful when debugging prompts or evaluating model performance. Because of these benefits, chain-of-thought prompting has become one of the most widely used techniques in modern prompt engineering. Effective prompt engineering follows several important best practices. These practices help ensure that AI models generate responses that are accurate, useful, and reliable. The first best practice is being clear and specific. Vague prompts often produce vague answers. Clearly stating what you want helps the model generate more precise outputs. For example, instead of asking, "Explain cloud computing," a better prompt might be, "Explain cloud computing in simple terms using 3 bullet points." Another important practice is providing context. Giving the model background information helps guide its response. Context helps the model understand the purpose of the task and produce more relevant answers. The third best practice is specifying the desired format. If you want the output in a particular format, such as bullet points, tables, or structured data, you should explicitly state that in the prompt. For example, you might ask the model to provide a response as a table with columns for advantages and disadvantages. Another important principle is iteration and refinement. Prompt engineering is rarely perfect on the first attempt. Users often experiment with different prompts, observe the results, and refine the prompt to improve the output. Through testing and iteration, prompts can be optimized to produce consistently high-quality responses. In this lesson, we explored the concept of prompt engineering and why it has become one of the most important skills when working with generative AI systems. Prompt engineering focuses on designing effective inputs that guide AI models toward producing useful and accurate outputs. Because generative AI systems rely heavily on prompts, the way a prompt is written can significantly influence the quality of the response. We first discussed how prompts influence AI behavior. Prompts provide the instructions and context that the model uses to generate its response. Clear prompts lead to more accurate and reliable outputs. Next, we explored different types of prompts, including instruction prompts, question prompts, and contextual prompts. Each type serves a different purpose depending on the task. We also examined prompt patterns, which are structured templates that guide AI responses. Role-based prompting is one example of a pattern that helps the model produce responses with a specific perspective or expertise. Another important concept we discussed was system prompts, which define the overall behavior and rules of an AI assistant. System prompts help ensure consistent behavior across conversations. We also explored few-shot prompting, which improves model performance by providing examples of the desired output. This technique helps the model understand the pattern it should follow. Finally, we discussed chain-of-thought prompting, which encourages the model to explain its reasoning step by step. This technique improves accuracy for complex tasks that require logical reasoning. Together, these techniques form the foundation of effective prompt engineering. In the next lesson, we will move from prompting techniques to building AI applications using cloud AI services. Amazon Bedrock is a fully managed service that enables developers to build, customize, and scale generative AI applications. It provides access to multiple foundation models through a unified API, making it easier for developers to integrate AI capabilities into their applications. Building AI applications on the One of the key features of Amazon Bedrock is its multi-model catalog. Instead of being limited to a single model provider, developers can choose from a range of models developed by different organizations. This allows teams to select the model that best fits their use case. Another important capability is serverless inference. With Bedrock, developers do not need to manage servers or compute infrastructure. The platform automatically handles capacity planning and scaling. This means applications can grow without requiring infrastructure changes. Security is another critical feature of Bedrock. The platform includes built-in enterprise security capabilities such as encryption, identity management, and network isolation. These features help organizations meet strict compliance and data protection requirements. Bedrock also integrates seamlessly with other AWS services. For example, developers can combine Bedrock with storage services, serverless compute, and machine learning tools to build full AI pipelines. By providing these capabilities in a single platform, Amazon Bedrock makes it significantly easier for organizations to build and deploy generative AI applications. Understanding the architecture of Amazon Bedrock helps developers design scalable and secure AI applications. The architecture consists of several layers, each responsible for a different part of the system. At the base layer are the foundation models. These models are developed by various AI providers and serve as the core intelligence behind generative AI applications. Building AI applications above the model layer is the API layer. This layer provides standardized APIs that allow developers to interact with foundation models. Instead of needing to understand the internal details of each model, developers simply send requests through these APIs. The next layer is the application layer. This is where developers integrate AI capabilities into real products such as chatbots, document processing systems, or AI assistants. The application layer interacts with the Bedrock APIs to send prompts and receive model responses. At the top of the architecture is the security and governance layer. This layer provides features such as identity management, encryption, access control, and logging. These capabilities ensure that AI applications remain secure and compliant with enterprise requirements. This layered architecture simplifies development because developers interact primarily with APIs, while the platform handles model management, infrastructure, and security behind the scenes. One of the most powerful capabilities of Amazon Bedrock is its multi-model catalog. Instead of being restricted to a single AI provider, developers can access models from several different organizations. Different models have different strengths. Some models are optimized for reasoning and long context tasks, while others may specialize in efficiency or domain-specific tasks. This flexibility is important because different applications require different models. For example, a model that performs well for creative writing may not be the best option for analyzing structured data or generating code. Multi-model access allows developers to experiment with different models and evaluate their performance using real application data. Teams can benchmark models against each other and choose the one that provides the best balance of accuracy, latency, and cost. Another advantage is reduced vendor lock-in. Because developers can switch between models without redesigning their applications, organizations maintain greater flexibility when building AI systems. By providing access to multiple foundation models in one platform, Bedrock enables organizations to optimize their AI applications more effectively. At the heart of every generative AI application is a process called model inference. Inference refers to the moment when a trained model generates an output in response to an input. In practical terms, inference occurs whenever a user interacts with an AI system. For example, when someone asks a chatbot a question, the system sends the prompt to a model, which processes the request and generates a response. The inference process typically follows several steps. First, a user submits a prompt through an application interface. This prompt is then sent to the AI platform, which routes the request to the appropriate foundation model. Next, the model analyzes the prompt and generates an output based on patterns it learned during training. Finally, the response is returned to the application and presented to the user. Inference powers many different types of AI tasks. These include text generation, document summarization, translation, question answering, and even code generation. Because inference happens every time a user interacts with an AI system, it is one of the most important processes to understand when building AI applications. Efficient inference workflows ensure that applications can respond quickly, handle many users simultaneously, and operate cost-effectively. In generative AI systems, one of the most important concepts to understand is model inference. Inference refers to the process where a trained AI model generates an output based on an input prompt. This process occurs every time a user interacts with an AI application. For example, when a user asks a chatbot a question, the system sends that prompt to a foundation model. The model processes the request, analyzes the context of the prompt, and generates a response. This entire process, from receiving the prompt to generating the final response, is known as inference. Inference is the core computational event behind nearly every generative AI interaction. Whether a system is summarizing documents, generating marketing content, translating text, or answering questions, the model is performing inference to produce the output. In a cloud environment, inference workflows are designed to be highly efficient and scalable. Applications send prompts to the AI platform, which then routes the request to the selected foundation model. The model processes the prompt and returns the generated response back to the application. Efficient inference workflows are critical for building responsive AI systems. Applications must be able to handle many requests simultaneously while maintaining fast response times. Cloud AI platforms address this challenge by automatically managing computing resources and scaling infrastructure as demand increases. Another important factor in inference is cost efficiency. Because inference occurs every time a model generates output, Optimizing inference workflows helps organizations control operational costs while maintaining high performance. Understanding inference is essential for developers building generative AI applications because it represents the moment where AI models actually deliver value to users. Now let's look at how inference works within the Amazon Bedrock environment. A typical Bedrock inference workflow follows a simple but powerful sequence of steps. The process begins when a user sends a prompt through an application interface. This prompt might be a question, a request to summarize a document, or an instruction to generate content. Next, the application sends the prompt to Amazon Bedrock through a secure API request. The request typically includes the prompt itself, as well as additional parameters such as the selected model and configuration settings. Once the request reaches Bedrock, the platform routes the request to the appropriate foundation model. Bedrock supports multiple models from different providers, so the system selects the model specified in the request. The selected model then performs inference, processing the prompt and generating an output. This output might be a paragraph of text, a summary, a classification result, or another type of response depending on the task. After the model generates the output, Bedrock returns the response to the application in real time. The application then displays the result to the user. This workflow enables developers to build real-time AI applications without needing to manage infrastructure or model deployments. Bedrock handles scaling, security, and model management behind the scenes. Because of this streamlined workflow, developers can focus on designing user experiences and building AI-powered features rather than managing complex machine learning systems. While large language models are powerful, they have one important limitation. Their knowledge is limited to the data they were trained on. This means their information may be outdated or incomplete. To address this challenge, many AI systems use knowledge bases. Knowledge bases allow AI applications to retrieve relevant information from external data sources before generating a response. These knowledge bases may include many different types of data. For example, organizations may index internal documents, policy manuals, product catalogs, support tickets, research papers, or structured databases. When a user asks a question, the system searches the knowledge base to find information related to the query. This information is then provided to the AI model as additional context. By retrieving relevant information from trusted data sources, the AI system can generate responses that are more accurate and up-to-date. Knowledge bases are particularly important in enterprise environments. Businesses often rely on AI systems to answer questions about internal processes, products, or policies. Without access to company-specific knowledge, the AI model would not be able to provide reliable answers. Using knowledge bases helps reduce errors and increases user trust in AI systems. One of the most important architectural patterns for building knowledge-based AI systems is retrieval augmented generation, commonly known as RAG. RAG combines the generative capabilities of foundation models with the precision of document retrieval systems. The process begins when a user submits a query. Instead of sending the query directly to the model, the system first performs document retrieval. This step searches a knowledge base for documents that are relevant to the user's question. Once the system identifies relevant documents, it extracts the most relevant sections of those documents. These sections are then added to the prompt that will be sent to the model. This step is called prompt augmentation. By including retrieved information in the prompt, the model receives additional context that helps it generate a more accurate response. Finally, the model generates a grounded response that incorporates both its trained knowledge and the retrieved documents. RAG offers several advantages. First, it improves accuracy by grounding responses in real documents rather than relying solely on model training data. Second, it allows knowledge to be updated without retraining the model. Organizations can update their knowledge bases independently, ensuring the AI system always uses the most current information. Third, RAG improves transparency. Because responses are based on retrieved documents, the system can show users where the information came from. This approach has become one of the most widely used architectures for enterprise AI applications. Organizations across many industries are now using Amazon Bedrock to build real-world generative AI applications. One common use case is intelligent chatbots. These systems can handle complex customer inquiries, provide support, and maintain context across multi-step conversations. Another popular application is document summarization. Businesses often deal with long reports, research papers, and legal documents. AI systems can automatically summarize these documents and highlight key insights. Bedrock is also used to build knowledge assistants. These assistants combine generative AI with knowledge bases to help employees quickly find answers within internal documentation. Another important use case is automated reporting. AI systems can generate structured reports based on data analysis, helping organizations produce insights more efficiently. These applications demonstrate how generative AI can improve productivity, reduce operational costs, and support better decision-making. Because Bedrock provides managed infrastructure, integrated security, and access to multiple foundation models, organizations can deploy these applications without building complex machine learning systems from scratch. As generative AI continues to evolve, platforms like Bedrock will play a key role in enabling organizations to build powerful AI-driven products and services. In the next lesson, we will explore responsible AI and AI governance, including topics such as bias mitigation, model safety, and compliance frameworks. In this lesson, we explored how organizations build generative AI applications using cloud-based AI platforms and foundation models. Modern AI development has shifted away from training models from scratch toward leveraging powerful pre-trained models that are accessible through managed services. One of the key technologies enabling this shift is Amazon Bedrock, which provides a fully managed platform for building and deploying generative AI applications. By offering access to multiple foundation models through a unified API, Bedrock allows developers to integrate AI capabilities into applications quickly and efficiently. We also discussed the architecture of Amazon Bedrock, which is organized into several layers. At the foundation are the AI models themselves, which provide the intelligence behind generative AI systems. Above that is the API layer, which provides standardized interfaces for interacting with those models. On top of the API layer sits the application layer, where developers build AI-powered applications such as chatbots, document summarization tools, and AI assistants. Finally, the security and governance layer ensures that applications meet enterprise requirements for identity management, encryption, and compliance. Another important concept we covered is model inference. Inference is the process of generating outputs from a trained model in response to user prompts. Every time a user interacts with an AI system, whether asking a question, requesting a summary, or generating content, the model performs inference to produce the response. We also explored how knowledge bases enhance AI systems. Because language models are limited by the data they were trained on, knowledge bases allow applications to retrieve relevant information from external data sources before generating a response. This approach improves the accuracy and relevance of AI-generated answers. Building on that idea, we introduced Retrieval Augmented Generation, or RAG. This architecture combines document retrieval with generative models to produce responses that are grounded in real information. RAG helps reduce hallucinations and ensures that AI systems provide responses based on verified data. Finally, we looked at several enterprise AI application patterns, including intelligent chatbots, document summarization systems, knowledge assistants, and automated reporting tools. Together, these concepts illustrate how cloud AI platforms like Bedrock make it possible to build scalable, production-ready generative AI applications. In the next lesson, we will explore responsible AI and AI governance, focusing on topics such as fairness, transparency, safety, and compliance in AI systems. Building reliable machine learning systems requires following a structured process known as the machine learning lifecycle. This lifecycle represents the stages that take a model from raw data to a production-ready system. The first stage is data collection. Machine learning models depend heavily on data, so collecting relevant and high-quality data is essential. Data may come from databases, applications, logs, sensors, or other digital systems. The next stage is data preparation. Raw data is rarely ready for training immediately. Data scientists must clean the data, remove errors, handle missing values, and transform the data into a format suitable for machine learning models. Once the data is prepared, the next stage is model training. During training, the machine learning algorithm analyzes the prepared dataset and learns patterns within the data. These patterns allow the model to make predictions about new data. After training, the model must go through evaluation. This step tests how well the model performs using validation datasets and test datasets. Evaluation ensures the model performs accurately and generalizes well to unseen data. Once the model has been validated, it moves to the deployment stage. Deployment makes the model available to applications so it can generate predictions in real-world environments. Each stage of the machine learning lifecycle builds upon the previous one. Skipping steps or rushing the process can lead to unreliable models and poor performance in production systems. By following a structured lifecycle, organizations can build machine learning systems that are accurate, reliable, and scalable. Data is the foundation of every machine learning system. The quality of the data used to train a model has a direct impact on the model's accuracy and reliability. Machine learning data can come from many different sources. Common data sources include databases and data lakes that store structured or unstructured information. Business applications such as CRM systems, financial platforms, and customer support systems also generate valuable data sets. Another important source of data is logs and sensor data. Many modern systems generate continuous streams of data that can be used for predictive modeling. For example, IoT devices, manufacturing equipment, and monitoring systems produce sensor data that can help train machine learning models. Once data has been collected, it must be prepared before it can be used for training. This step is called data preparation. Data preparation often begins with cleaning the data. This includes removing duplicate records, correcting errors, and handling missing values. Poor quality data can significantly reduce model performance. Another important step is feature engineering. Feature engineering involves selecting and transforming variables that help the model understand patterns in the data. Finally, data transformation may be required to convert the dataset into the format expected by machine learning algorithms. This might include normalization, encoding categorical variables, or splitting datasets into training and validation sets. Effective data preparation ensures that the machine learning model can learn meaningful patterns and produce accurate predictions. Model training is the stage where a machine learning algorithm learns patterns from data. During this phase, the model analyzes the training dataset and adjusts its internal parameters to minimize prediction errors. The training process usually begins by selecting an appropriate algorithm. Different algorithms are designed for different types of problems, such as classification, regression, or clustering. Once an algorithm has been selected, the next step is to feed the training data into the model. The algorithm processes the data and identifies patterns that relate input features to the target outcome. As the model processes the data, it continuously adjusts its internal parameters to improve performance. This process is known as optimization. The goal of optimization is to minimize the difference between the model's predictions and the actual results in the dataset. Training can be computationally intensive, especially when working with large datasets or complex models such as deep neural networks. This is where cloud platforms like AWS become extremely valuable. AWS provides on-demand computing resources that allow developers to train models using powerful hardware without maintaining their own infrastructure. By leveraging scalable cloud resources, organizations can experiment with different models, train large datasets, and accelerate the development of machine learning systems. After a machine learning model has been trained, it must be evaluated before being deployed into production. Model evaluation determines how well the model performs and whether it can make accurate predictions on new data. Evaluation typically involves testing the model using datasets that were not used during training. These datasets help measure how well the model generalizes to unseen data. One common approach is to use a validation dataset during training. The validation dataset helps tune model parameters and improve performance. Another important dataset is the test dataset. The test dataset is used after training to perform a final evaluation of the model's performance. Another technique used in evaluation is cross-validation. Cross-validation involves splitting the dataset into multiple segments and testing the model across several training and validation cycles. This helps produce more reliable performance measurements. Several metrics are commonly used to measure model performance. These include accuracy, precision, recall, and the F1 score. Each metric provides a different perspective on how well the model performs. Model evaluation ensures that the system performs reliably before it is deployed into production environments. In the next section, we will explore the differences between training and inference, which represent the two main phases of machine learning systems. Machine learning systems operate in two primary phases: training and inference. Understanding the difference between these two stages is essential for designing scalable machine learning applications. The training phase is when the model learns patterns from historical data. During training, the algorithm processes large datasets and adjusts internal parameters to minimize prediction errors. This process can be computationally expensive because the model may need to process millions or even billions of data points. Training typically occurs periodically rather than continuously. For example, a company might retrain a model once a week or once a month using updated data. Because of the heavy computational demand, training often runs on powerful cloud infrastructure such as GPU or distributed computing clusters. Once the model has been trained, it enters the inference phase. Inference is the process of using the trained model to make predictions on new data. Unlike training, inference must often happen in real time. For example, when a user submits a request to a recommendation system, fraud detection system, or chatbot, the model performs inference to generate a prediction or response. Inference workloads are usually less computationally intensive than training, but they require fast response times and high availability. This is because applications may need to process thousands or millions of prediction requests every second. Because training and inference have different computational requirements, many machine learning systems separate these two processes into different infrastructure environments. Training systems focus on large-scale computation, while inference systems focus on low latency predictions. Understanding this distinction helps organizations design efficient machine learning architectures. After a machine learning model has been trained and evaluated, the next step is model deployment. Deployment is the process of making the model available for real-world use, so applications can generate predictions using the model. In many systems, deployed models are exposed through application programming interfaces, or APIs. These APIs allow applications to send input data to the model and receive predictions as responses. For example, an e-commerce website might send customer data to a recommendation model through an API. The model processes the request and returns recommended products. Another deployment strategy is batch processing pipelines. In this approach, models process large datasets at scheduled intervals rather than responding to individual requests in real time. Batch processing is often used for tasks such as generating reports, scoring large datasets, or updating analytics dashboards. Some machine learning models are also deployed directly to edge devices. These models run locally on devices such as smartphones, IoT devices, or embedded systems. This approach allows predictions to be generated without sending data to the cloud. Effective deployment ensures that machine learning models operate reliably, securely, and at scale within production environments. A production machine learning system involves more than just a trained model. It requires a complete deployment architecture designed to ensure reliability, scalability, and observability. At the core of this architecture is the inference layer. This layer is responsible for serving predictions to applications. When a user request arrives, the inference service processes the request and generates the model's output. Surrounding the inference layer is the data and integration layer. This layer handles the flow of data between applications, databases, and machine learning services. It ensures that incoming data is correctly formatted and delivered to the model. The outer layer of the architecture focuses on observability and monitoring. Monitoring tools track system performance, detect failures, and generate alerts when issues occur. These monitoring systems measure important operational metrics such as latency, throughput, and error rates. This information helps teams identify performance problems and maintain system reliability. By separating machine learning systems into multiple layers, organizations can design architectures that are easier to maintain, scale, and troubleshoot. Once a machine learning model has been deployed, the work is not finished. Models must be continuously monitored and maintained to ensure they continue performing accurately over time. One important concept in model maintenance is prediction accuracy monitoring. Over time, the performance of a model may decline as real-world conditions change. Monitoring systems track prediction quality and compare current results to baseline performance. Another important challenge is data drift. Data drift occurs when the distribution of incoming data changes compared to the data used during training. When this happens, the model may begin producing inaccurate predictions. Monitoring tools can detect data drift by analyzing statistical patterns in the incoming data. Operational monitoring is also essential. Machine learning systems must maintain reliable infrastructure, including low latency, high throughput, and stable availability. If monitoring systems detect declining performance or data drift, organizations may need to retrain the model using updated datasets. Retraining allows the model to learn new patterns and maintain prediction accuracy. Continuous monitoring and maintenance ensure that machine learning systems remain reliable in real-world environments. In this lesson, we explored the core concepts behind building and deploying machine learning systems using cloud infrastructure. First, we examined the machine learning lifecycle, which includes stages such as data collection, data preparation, model training, evaluation, deployment, and monitoring. Each stage plays an important role in ensuring that machine learning systems operate reliably in production environments. We then explored the importance of data preparation, which involves cleaning datasets, engineering features, and transforming raw data into a format suitable for machine learning models. High-quality data is essential for building accurate models. Next, we discussed model training, where algorithms learn patterns from training data by adjusting internal parameters. This process often requires significant computational resources, which cloud platforms like AWS provide on demand. We also examined model evaluation, which ensures that models generalize well to new data using techniques such as validation datasets, test datasets, and cross-validation. Another key concept is the distinction between training and inference. Training involves learning patterns from historical data, while inference involves generating predictions from new inputs. Finally, we explored how machine learning models are deployed and monitored in production systems. Deployment allows applications to access models through APIs, batch pipelines, or edge devices, while monitoring ensures models remain accurate and reliable over time. Together, these concepts form the foundation of building scalable machine learning systems on AWS. In the next lesson, we will explore responsible AI and AI governance, including how organizations ensure fairness, transparency, and safety in AI systems. Pre-built AI services are ready-to-use machine learning models delivered through cloud APIs. These services allow developers to access advanced AI capabilities without training models or managing infrastructure. Instead of building machine learning models from scratch, developers simply send requests to the service through an API. The service processes the input using its trained machine learning models and returns a response. These services support a wide variety of AI capabilities. One common category is image recognition, where AI systems analyze images or videos to identify objects, people, or scenes. Another category is natural language processing, which enables applications to analyze and understand human language. NLP services can detect sentiment, extract entities, or identify key phrases within text. Pre-built AI services also support speech synthesis, which allows applications to convert text into natural-sounding speech. This capability is used in voice assistants, customer service systems, and accessibility tools. Another important capability is conversational AI, which allows developers to build chatbots and voice assistants that interact with users using natural language. Because these services are already trained and optimized, developers can integrate powerful AI capabilities into their applications quickly and easily. AWS provides a large ecosystem of AI services that address some of the most common AI use cases in modern applications. One major category is computer vision, which allows applications to analyze images and videos. AWS provides this capability through services such as Amazon Recognition. Another important category is natural language processing, which enables applications to understand and analyze text. AWS offers this functionality through services like Amazon Comprehend. AWS also provides tools for conversational AI, which enable developers to build chatbots and voice-based assistants. These systems can understand user intent and maintain multi-step conversations. In addition, AWS offers speech generation services that convert written text into realistic speech. These services allow applications to provide audio responses to users. Together, these categories form a powerful ecosystem that allows developers to integrate advanced AI capabilities into applications without building complex machine learning models themselves. This ecosystem allows organizations to build intelligent systems for customer support, content analysis, automation, and many other applications. Amazon Recognition is a fully managed computer vision service that allows applications to analyze images and videos automatically. Computer vision is a branch of artificial intelligence that enables machines to interpret visual information. Recognition makes it possible for applications to understand the contents of images and videos at scale. One of the core capabilities of recognition is object detection. The service can identify thousands of different objects and scenes within images. Another capability is facial recognition. Recognition can detect and analyze faces within images or video streams. This functionality can be used for applications such as identity verification or access control. Recognition can also perform scene analysis, allowing applications to understand the environment shown in an image or video. Another important capability is content moderation. Recognition can automatically detect inappropriate or unsafe visual content. This is commonly used by social media platforms and online communities to moderate uploaded content. Because recognition runs on AWS infrastructure, it can process very large volumes of images and video frames efficiently. Amazon Recognition is used in many real-world applications that require analyzing large volumes of visual data. One common use case is security and surveillance systems. Organizations use recognition to detect faces and identify objects in video feeds. This allows security systems to automatically monitor environments and detect unusual activity. Another important use case is content moderation. Online platforms often receive millions of images and videos uploaded by users. Recognition can automatically analyze this content and flag images that contain inappropriate material. Recognition is also used in retail analytics. Retailers can analyze customer movement and behavior within stores using computer vision systems. This helps businesses understand customer patterns and optimize store layouts. Another application is media indexing. Large media libraries often contain thousands of images and videos. Recognition can automatically tag and categorize visual content, making it easier to search and organize large media collections. One of the key advantages of recognition is its ability to process large amounts of visual data automatically using a single API call. This allows organizations to analyze millions of images or video frames quickly and efficiently. Another important AWS AI service is Amazon Comprehend, which focuses on analyzing and understanding human language. Amazon Comprehend is a managed natural language processing service that allows applications to extract insights from large volumes of text. Natural language processing, often abbreviated as NLP, is a branch of artificial intelligence that enables computers to understand and interpret human language. Organizations today generate massive amounts of textual data through emails, documents, support tickets, customer reviews, and social media content. Analyzing this information manually is extremely difficult and time-consuming. Amazon Comprehend automates this process by analyzing text and identifying meaningful patterns and insights. One of its key capabilities is sentiment analysis. Sentiment analysis determines whether text expresses positive, negative, neutral, or mixed emotions. Businesses commonly use this capability to analyze customer feedback and measure customer satisfaction. Another powerful feature is entity recognition. This allows Comprehend to identify important entities in text, such as people, organizations, locations, and dates. Entity recognition helps organizations structure unstructured data and extract meaningful information from large text datasets. Comprehend also provides key phrase extraction, which identifies the most important phrases or topics within a document. This capability is useful for summarizing content or identifying key themes in large datasets. Another feature is language detection. Amazon Comprehend can automatically identify the language used in a piece of text, supporting more than 100 languages. Because Comprehend is fully managed, developers can access these capabilities through simple API calls without needing to build or train their own NLP models. Amazon Comprehend is widely used across industries to automate text analysis and extract valuable insights from large datasets. One common use case is customer feedback analysis. Businesses receive large amounts of feedback through product reviews, surveys, and support tickets. Comprehend can analyze this feedback and identify sentiment trends, helping organizations understand customer satisfaction and identify areas for improvement. Another important application is document classification. Many organizations manage large collections of documents such as legal files, contracts, and reports. Comprehend can automatically categorize documents based on their content, making it easier to organize and retrieve information. Amazon Comprehend is also useful for fraud detection. Financial institutions and online platforms often monitor large volumes of communication data. By analyzing language patterns, Comprehend can help identify suspicious activity or fraudulent behavior. Another use case is business intelligence. Many organizations rely on data analysis to guide decision-making. Comprehend can extract insights from unstructured text data, helping analysts identify trends and patterns that would otherwise be difficult to detect. Because these capabilities operate through scalable cloud infrastructure, Comprehend can analyze millions of documents quickly and efficiently. This allows organizations to turn unstructured text into structured insights that support better decision-making. Another important AWS AI service is Amazon Lex, which enables developers to build conversational interfaces such as chatbots and voice assistants. Amazon Lex uses the same underlying deep learning technology that powers Amazon Alexa. This technology allows systems to understand natural language and interpret user intent. One of the key capabilities of Amazon Lex is natural language understanding. This allows the system to interpret what a user is trying to accomplish based on their words, even when the phrasing varies. For example, a user might ask a chatbot to check my order status, track my package, or where is my delivery? Although the wording is different, the intent is the same. Amazon Lex can recognize these variations and respond appropriately. Another important capability is multi-turn dialogue management. This allows chatbots to maintain context throughout a conversation. Instead of answering isolated questions, the system can guide users through complex interactions, such as booking reservations or troubleshooting problems. Amazon Lex supports both voice and text interfaces. This means developers can create chatbots for messaging platforms, websites, mobile applications, or voice-based systems. By providing these capabilities as a managed cloud service, Amazon Lex allows developers to build sophisticated conversational systems without developing complex natural language models from scratch. Amazon Polly is a cloud-based text-to-speech service that converts written text into natural-sounding human speech. Text-to-speech technology is widely used in applications such as voice assistants, accessibility tools, automated customer service systems, and interactive media applications. Amazon Polly allows developers to convert text into audio using realistic voices generated by deep learning models. These voices sound natural and expressive, making interactions with applications more engaging. One of Polly's key capabilities is support for multiple languages and voices. The service provides dozens of voices across many different languages, allowing applications to support users around the world. Another feature is customizable speech output. Developers can adjust factors such as speaking speed, pitch, and pronunciation. This allows applications to tailor the audio experience for different use cases. Amazon Polly also supports real-time streaming audio, enabling applications to generate speech quickly and deliver responses with low latency. Because Polly operates through simple API calls, developers can easily integrate speech generation into applications such as chatbots, voice assistants, or interactive learning platforms. By converting text into natural speech, Polly helps make applications more accessible and interactive. In this lesson, we explored several pre-built AI services offered by AWS and how they enable developers to integrate artificial intelligence capabilities into applications quickly and efficiently. We began by discussing the concept of pre-built AI services, which provide ready-to-use machine learning models accessible through APIs. These services eliminate the need for developers to train or manage machine learning models themselves. We then explored 4 key AWS AI services. First, Amazon Recognition, which provides computer vision capabilities for analyzing images and videos. Recognition can detect objects, analyze scenes, recognize faces, and moderate visual content. Next, we discussed Amazon Comprehend, a natural language processing service that analyzes text. Comprehend can perform sentiment analysis, extract entities and key phrases, and detect languages within text data. We also explored Amazon Lex, which enables developers to build conversational AI systems such as chatbots and voice assistants. Lex can interpret user intent and manage multi-step conversations. Finally, we discussed Amazon Polly, which converts written text into natural-sounding speech. Polly enables applications to communicate with users using realistic voice output. Together, these services allow organizations to quickly build intelligent applications without the complexity of developing machine learning models from scratch. By leveraging AWS AI services, developers can focus on building innovative products while relying on scalable cloud infrastructure to handle the underlying machine learning capabilities. In the next lesson, we will explore responsible AI and AI governance on AWS, including how organizations ensure fairness, transparency, and safety in AI systems. Natural language processing is a branch of artificial intelligence that focuses on enabling computers to work with human language. Unlike structured data, which is neatly organized into tables and databases, natural language is complex and ambiguous. Words can have multiple meanings depending on context, and human language often contains slang, abbreviations, and incomplete sentences. NLP systems must therefore learn to interpret language in a way that approximates human understanding. To accomplish this, NLP models analyze patterns within large datasets of text. These models learn relationships between words, phrases, and concepts. By identifying these patterns, NLP systems can perform tasks such as classifying text, identifying key entities, or determining the sentiment of a sentence. Organizations increasingly rely on NLP because large amounts of valuable information exist in unstructured text data. For example, businesses receive thousands of customer reviews each day. Government agencies process massive volumes of documents. Healthcare organizations manage patient notes and medical records. Without automated analysis tools, extracting insights from these datasets would be extremely difficult. NLP enables organizations to transform unstructured text into structured data that can be analyzed and used for decision-making. Modern NLP systems are often powered by machine learning models and deep learning architectures, which enable them to understand language more accurately than traditional rule-based systems. One of the main reasons NLP has become so important is that text data exists everywhere in modern organizations. Companies generate massive amounts of text every day across many different channels. Customer reviews provide feedback about products and services. Emails and internal reports contain important operational information. Social media platforms generate enormous streams of user-generated text, including comments, posts, and discussions. Customer support systems also produce large volumes of text through support tickets and chat transcripts. All of this information represents a valuable source of organizational intelligence. However, analyzing this data manually is not practical. A company may receive tens of thousands or even millions, of pieces of text data every day. NLP systems allow organizations to process this information automatically. For example, an NLP system could analyze customer reviews and identify common complaints about a product. It could detect emerging trends in social media conversations or identify urgent issues in customer support tickets. This ability to extract insights from text data allows organizations to make faster and better decisions. By leveraging cloud-based NLP services, businesses can analyze large volumes of text data quickly and efficiently without building complex machine learning systems themselves. AWS provides several powerful services that help developers build NLP-powered applications quickly. One of the most widely used services is Amazon Comprehend. This service analyzes text and extracts useful insights such as sentiment, entities, and key phrases. Another important service is Amazon Textract, which extracts text and structured data from scanned documents. This allows organizations to digitize and analyze information contained in forms, invoices, and reports. AWS also provides Amazon Bedrock, which gives developers access to foundation models capable of advanced language generation and reasoning. Another key service is Amazon Lex, which allows developers to build conversational interfaces such as chatbots and voice assistants. Together, these services provide a powerful ecosystem for building NLP applications. Developers can combine these tools to build systems that analyze documents, answer questions, automate workflows, and provide intelligent customer support. Because these services are fully managed, developers can focus on building applications rather than training machine learning models or managing infrastructure. One of the most important NLP techniques is entity extraction, also known as named entity recognition. Entity extraction identifies important pieces of information within unstructured text and converts them into structured data. For example, entities might include people, organizations, locations, or dates. Imagine the sentence, Amazon announced a new AI service in Seattle in 2024. An entity extraction system would identify Amazon as an organization, Seattle as a location, and 2024 as a date. This process allows machines to automatically structure information from raw text. Entity extraction is extremely useful in many applications. News organizations use it to analyze articles and identify key individuals and events. Financial institutions use it to extract company names and financial data from reports. Businesses also use entity extraction to analyze customer feedback and identify products, brands, or locations mentioned in reviews. By transforming unstructured text into structured information, entity extraction makes it easier for organizations to analyze large data sets and extract meaningful insights. Now let's look at how entity extraction works in practice. Entity extraction, also known as named entity recognition, automatically identifies important entities in text and categorizes them into predefined groups such as people, organizations, locations, or dates. Consider the example sentence. Amazon announced a new AI service in Seattle in 2024. An NLP system analyzing this sentence would detect several entities. It would identify Amazon as an organization, Seattle as a location, and 2024 as a date. This process may seem simple, but it requires sophisticated machine learning models trained on large data sets of text. These models learn how entities appear in different contexts and how language patterns signal the presence of specific entity types. The key advantage of entity extraction is that it converts unstructured text into structured data. For example, instead of storing a paragraph of text that must be read manually, systems can automatically extract key entities and store them as structured information in databases. This makes it easier to search, analyze, and organize information. Many industries rely heavily on entity extraction. Financial organizations use it to detect company names and financial events in news articles. Healthcare systems use it to extract medical terms from clinical notes. Legal teams use it to identify people, organizations, and dates within contracts. Because entity extraction can process thousands or even millions of documents automatically, it significantly reduces the amount of manual work required to analyze text data. Another key NLP capability is sentiment analysis, which determines the emotional tone of text. Sentiment analysis helps systems understand whether a piece of text expresses a positive, negative, neutral, or mixed sentiment. For example, a product review that says, "This phone has an amazing battery life," would likely be classified as positive sentiment. On the other hand, a review stating, "The device stopped working after 1 week," would be classified as negative sentiment. Sentiment analysis is particularly useful for organizations that need to monitor large volumes of customer feedback. Businesses receive feedback from many channels, including product reviews, customer surveys, social media comments, and support interactions. Manually analyzing this feedback would require enormous effort. Sentiment analysis automates this process by analyzing text and assigning sentiment scores. These scores allow companies to quickly understand how customers feel about their products or services. Another advantage of sentiment analysis is that it can track sentiment trends over time. For example, a company launching a new product can monitor whether public opinion becomes more positive or negative after the launch. By automatically analyzing emotional tone, sentiment analysis provides organizations with valuable insights into customer perception and brand reputation. Sentiment analysis is used across many industries to understand opinions and public perception. One common use case is customer feedback analysis. Companies analyze product reviews and support interactions to understand what customers like and dislike about their products. By analyzing sentiment across thousands of reviews, organizations can quickly identify recurring problems or popular features. Another important application is brand monitoring. Companies track social media conversations to understand how people perceive their brand. Sentiment analysis can detect changes in public opinion and alert organizations to potential reputation risks. Sentiment analysis is also useful for product insights. By analyzing customer feedback, companies can identify which product features generate the most positive responses and which features need improvement. In financial markets, sentiment analysis is sometimes used to analyze news articles and social media posts related to companies or industries. This information can help analysts understand market sentiment. Because sentiment analysis can process large volumes of text quickly, it provides organizations with a scalable way to measure opinions across many communication channels. Another powerful application of NLP is document analysis. Organizations often manage large collections of complex documents, such as contracts, financial reports, invoices, and research papers. Analyzing these documents manually can be slow and error-prone. AI-powered document analysis systems can automatically extract information from documents and convert it into structured data. For example, an AI system analyzing invoices could extract important fields such as invoice number, payment date, vendor name, and total amount. Similarly, contract analysis systems can identify key clauses, dates, and obligations within legal documents. In financial institutions, document analysis can be used to process loan applications or regulatory filings. In healthcare, NLP systems can analyze patient records and medical notes to extract relevant clinical information. By automating document analysis, organizations can process large volumes of information more efficiently and reduce manual workload. These systems also improve accuracy by ensuring that critical data is extracted consistently across documents. Building an NLP system typically involves several stages that together form an NLP processing pipeline. The pipeline begins with text ingestion, where raw text data is collected from sources such as documents, databases, or APIs. Next comes text pre-processing, where the text is cleaned and prepared for analysis. This step may involve removing unnecessary characters, normalizing text, and tokenizing sentences into words. After pre-processing, the system performs tasks such as entity extraction and sentiment analysis. These steps transform raw text into structured insights that can be used by applications or analytics systems. For example, entity extraction identifies key entities within the text, while sentiment analysis determines the emotional tone. Once these insights are extracted, the information can be stored in databases or used by applications such as dashboards, search engines, or recommendation systems. Each stage of the NLP pipeline adds structure and meaning to the data. By the end of the pipeline, unstructured text has been transformed into structured, actionable insights that organizations can use for decision-making. In this lesson, we explored how natural language processing enables machines to understand and analyze human language. We began by introducing the fundamentals of NLP and discussing why analyzing text data has become increasingly important. Organizations generate large volumes of text through reviews, emails, reports, and social media interactions. We then explored entity extraction, which identifies important entities within text, such as people, organizations, locations, and dates. This technique converts unstructured text into structured information that can be easily analyzed. Next, we discussed sentiment analysis, which determines the emotional tone of text. Sentiment analysis allows organizations to monitor customer satisfaction, analyze feedback, and track brand perception. We also examined document analysis, where AI systems extract insights and structured information from complex documents such as contracts, invoices, and reports. Finally, we looked at the NLP pipeline architecture, which transforms raw text into actionable insights through stages such as ingestion, pre-processing, entity extraction, and sentiment analysis. Together, these techniques allow organizations to analyze massive amounts of text data automatically. In the next lesson, we will explore computer vision and image AI on AWS, where we will learn how AI systems analyze images and videos to understand visual information. Computer vision has become increasingly important because the amount of visual data produced every day is growing rapidly. Many industries generate enormous amounts of image and video data. Security cameras produce continuous video streams. Smartphones and social media platforms generate millions of photos every day. Medical institutions produce imaging data such as X-rays and MRI scans. Analyzing this visual data manually would be extremely time-consuming and inefficient. Computer vision systems solve this problem by automatically analyzing images and videos. For example, in security and surveillance systems, computer vision can detect suspicious activities or identify unauthorized individuals in real time. In healthcare, computer vision is used to analyze medical images such as X-rays or CT scans. AI systems can assist doctors by identifying patterns that may indicate disease. Computer vision also plays a critical role in autonomous vehicles. Self-driving cars rely on computer vision systems to detect road signs, pedestrians, vehicles, and other obstacles. Another important application is retail analytics. Stores use cameras and computer vision systems to monitor shelf inventory, analyze customer behavior, and optimize store layouts. Because visual data continues to grow rapidly, automated computer vision systems are becoming essential tools across many industries. AWS provides a variety of services that allow developers to build computer vision applications quickly and efficiently. One of the most widely used services is Amazon Rekognition, which provides pre-built computer vision capabilities for for analyzing images and videos. Recognition can detect objects, recognize faces, analyze scenes, and even moderate visual content. Another important service is Amazon SageMaker, which allows developers to build, train, and deploy custom machine learning models. This service is useful when organizations need specialized computer vision models tailored to their specific datasets. AWS also offers Amazon Textract, which extracts text and structured data from scanned documents. Textract combines computer vision with natural language processing to analyze forms, invoices, and reports. Another emerging capability comes from Amazon Bedrock, which provides access to foundation models capable of advanced reasoning and generative AI capabilities that can work with visual data. Together, these services provide developers with a powerful ecosystem for building computer vision applications. Instead of building complex machine learning systems from scratch, developers can leverage AWS tools to integrate computer vision into applications quickly. One of the most fundamental techniques in computer vision is image classification. Image classification involves analyzing an image and assigning it to a category based on its dominant visual content. For example, an image classification system might determine whether an image contains a cat or a dog. Similarly, a system could classify images based on vehicle types, such as cars, bicycles, or motorcycles. Another example is scene classification. An image might be classified as representing an indoor environment, an outdoor landscape, or a city street. Image classification models learn these categories by training on large data sets of labeled images. During training, the model learns patterns that distinguish different categories. Once the model has learned these patterns, it can analyze new images and predict the most likely category. Image classification is widely used in many real-world applications. For example, social media platforms use image classification to organize photos automatically. Retail platforms use it to categorize product images. Medical imaging systems use classification to detect patterns in scans. Because image classification can process large numbers of images automatically, it helps organizations manage and analyze visual data more efficiently. To better understand how image classification works, let's walk through a simple example. Imagine we have an image of a dog running in a park. When the image is processed by a computer vision model, the system analyzes patterns in the image. These patterns may include shapes, textures, colors, and spatial relationships between objects. Based on these features, the model determines that the main subject of the image is a dog. The system may also detect that the environment appears to be an outdoor park. The system then assigns labels such as dog, animal category park, outdoor environment. These labels allow the image to be categorized automatically. This capability is extremely useful in large-scale image systems. For example, a photo storage platform containing millions of images could automatically categorize images based on their contents. Users could then search for images using terms such as dog, beach, or mountains, and the system would retrieve relevant images automatically. Image classification therefore provides a powerful way to transform raw visual data into structured information that applications can understand and use. Another major technique in computer vision is object detection. While image classification assigns a single label to an entire image, object detection goes a step further by identifying multiple objects within an image and determining where they are located. For example, imagine a street scene containing pedestrians, vehicles, bicycles, and traffic lights. An image classification model might label the image simply as street scene. However, an object detection model can identify each individual object within that image and locate them using bounding boxes. This means the system could detect a person, a car, a bicycle, and a traffic light, all within the same frame. Each detected object would also have coordinates indicating its position within the image. Object detection models work by scanning images and identifying visual patterns associated with specific objects. Modern systems typically rely on deep learning models such as convolutional neural networks to detect these patterns. The ability to identify multiple objects simultaneously makes object detection extremely useful for many real-world applications. For example, surveillance systems can automatically detect people or vehicles in camera feeds. Autonomous vehicles rely on object detection to identify pedestrians, road signs, and other obstacles. Another example is retail analytics, where cameras can monitor shelves and detect whether products are out of stock. Because object detection provides both object identity and object location, it enables machines to understand scenes in much greater detail than simple classification models. Object detection plays a crucial role in many modern technologies because it enables machines to monitor environments automatically. One of the most common applications is security and surveillance. Camera systems equipped with object detection can automatically detect suspicious activities or unauthorized individuals. For example, a system might trigger an alert if a person enters a restricted area. Another important application is autonomous vehicles. Self-driving cars rely heavily on computer vision systems to identify objects on the road. These systems must continuously detect pedestrians, other vehicles, road signs, and obstacles in real time. Object detection is also widely used in retail analytics. Cameras placed in stores can monitor shelves and automatically detect when products are missing or misplaced. This allows retailers to manage inventory more efficiently. In manufacturing, object detection is used for quality inspection. Cameras monitor production lines and detect defects in products. This allows companies to identify issues early and reduce waste. These applications demonstrate how object detection enables machines to monitor environments continuously and provide real-time insights. As visual data continues to increase across industries, automated detection systems are becoming essential tools for improving safety, efficiency, and operational awareness. Another powerful computer vision capability is face recognition. Face recognition systems analyze facial features to identify or verify individuals. These systems rely on machine learning models trained to recognize patterns in facial structures, such as the distance between eyes, shape of the nose, and contours of the face. Face recognition typically involves three main steps. The first step is face detection, where the system identifies the presence of faces within an image or video frame. The second step is face comparison, where the detected face is compared to faces stored in a database. This allows the system to determine whether the detected face matches a known individual. The final step is identity verification, where the system confirms whether the detected face belongs to the person it claims to represent. Because each human face has unique features, face recognition systems can accurately identify individuals in many situations. However, these systems must also be designed carefully to ensure privacy, fairness, and ethical use. When used responsibly, face recognition can provide powerful capabilities for identity verification and security systems. Face recognition technology is widely used in many applications where identity verification is important. One common use case is access control systems. Many buildings now use facial recognition technology to grant access to authorized individuals. Instead of using keycards or passwords, employees can simply look at a camera to verify their identity. Another major application is airport security. Many airports use facial recognition systems during passenger screening and boarding. These systems help verify passenger identities and improve security procedures. Face recognition is also widely used in smartphone authentication. Many smartphones allow users to unlock their devices using facial recognition. This provides a convenient and secure authentication method. Another common use case is photo tagging in social media platforms. Social media applications can automatically recognize individuals in photos and suggest tags for users. These examples demonstrate how face recognition systems can simplify identity verification and improve user experiences. However, because these systems involve sensitive biometric data, they must be implemented with strong privacy protections and responsible AI practices. In this lesson, we explored the fundamentals of computer vision and how AI systems analyze images and videos to understand visual information. We began by introducing the core concept of computer vision, which enables machines to interpret visual data in a way similar to human perception. We then explored image classification, where a model assigns a category label to an image based on its dominant content. This technique is widely used for organizing and categorizing visual data. Next, we discussed object detection, which identifies and locates multiple objects within a single image. Object detection enables systems to analyze scenes in greater detail and is widely used in surveillance systems, autonomous vehicles, and manufacturing. We also examined face recognition, which allows systems to detect, compare, and verify individuals based on facial features. This technology is used in access control systems, airport security, and smartphone authentication. Together, these techniques form the foundation of modern computer vision systems. Computer vision technologies allow organizations to analyze massive amounts of visual data automatically and extract valuable insights. In the next lesson, we will explore responsible AI and ethical AI systems on AWS, including how organizations ensure that AI technologies are developed and used responsibly. Chatbots are one of the most common forms of conversational AI. A chatbot is a software application designed to simulate human conversation and assist users through automated interactions. Chatbots can be deployed across many different platforms. Businesses often integrate chatbots into messaging platforms such as WhatsApp, Slack, or Microsoft Teams. They also appear on websites as live chat assistants that help visitors find information or resolve issues. Mobile applications frequently include chatbots that guide users through tasks or provide support within the app. Voice interfaces can also function as conversational systems when users interact through speech rather than text. The goal of a chatbot is to make services and information easier to access. Instead of navigating multiple pages or searching through menus, users can simply ask the chatbot a question. Early chatbots relied on predefined rules and keyword matching. These rule-based systems could only respond to specific phrases and struggled to handle complex language. Modern chatbots use artificial intelligence to interpret natural language. By analyzing the meaning of user input, these systems can understand requests even when users phrase them in different ways. Because chatbots can operate continuously without human intervention, they are widely used to automate customer service and support operations. Modern chatbots are capable of performing many tasks that traditionally required human assistance. One common capability is answering frequently asked questions. Organizations often receive large numbers of similar inquiries about products, services, or policies. Chatbots can instantly respond to these questions and provide accurate information. Chatbots are also widely used for customer support automation. They can guide users through troubleshooting steps, help resolve common problems, and escalate complex issues to human agents when necessary. Another important use case is scheduling and appointment management. For example, chatbots can allow users to book meetings, reserve restaurant tables, or schedule medical appointments. In e-commerce environments, chatbots often function as virtual shopping assistants. They can recommend products, answer questions about product features, and guide customers through the purchasing process. Because chatbots can handle multiple interactions simultaneously, they allow organizations to scale their support operations efficiently. By automating repetitive interactions, chatbots reduce the workload on human agents and allow them to focus on more complex or sensitive issues. Conversational AI systems rely on several components that work together to transform user messages into meaningful responses. The process begins with user input, which may come in the form of text messages or spoken language. Next, the system uses natural language processing to analyze the message. NLP techniques help identify key words, phrases, and the overall meaning of the input. Once the language has been analyzed, the system performs intent detection. Intent detection determines what the user is trying to accomplish. For example, the system might recognize that the user wants to book a flight, check an order status, or request technical support. After identifying the intent, the system uses dialogue management to determine how the conversation should continue. Dialogue management keeps track of context and ensures that the conversation flows logically. Finally, the system generates a response. This response may provide information, ask follow-up questions, or perform an action on behalf of the user. Together, these components allow conversational AI systems to conduct intelligent and structured interactions with users. While technology is essential for conversational AI, design plays a critical role in creating effective interactions. Conversational design focuses on how AI systems communicate with users and how conversations are structured. One key design principle is clarity. Messages should be simple and easy to understand so users always know how to respond. Another principle is natural flow. Conversations should progress logically and feel similar to human dialogue rather than rigid system commands. Helpfulness is also an important aspect of conversational design. The goal of a conversational system is to assist users in solving problems efficiently. Responses should provide meaningful guidance rather than generic replies. Finally, conversational systems should minimize friction. Users should be able to complete tasks quickly without unnecessary steps or repeated questions. When conversational design is done well, interactions feel smooth and intuitive. The technology becomes almost invisible, and users simply experience a helpful conversation that solves their problem. A core capability of conversational AI systems is intent recognition. Intent recognition refers to the system's ability to determine what a user wants to accomplish when they send a message. When a user interacts with a chatbot or voice assistant, their message may contain many words, but behind those words is usually a specific goal or action. Intent recognition helps the system understand that goal. For example, imagine a user says, "I want to book a flight to New York." The system must analyze this message and determine that the user's intent is booking a flight. Even if the user phrases the request differently, such as, "Find me a flight to New York," or "I need to travel to New York," the system should still recognize the same intent. Intent recognition is powered by natural language understanding models that analyze patterns in text and learn how users express requests in different ways. Once the system correctly identifies the user's intent, it can determine the appropriate next step. This may involve asking follow-up questions, retrieving information, or executing an action. Accurate intent recognition is essential for conversational AI systems because it ensures that the system responds correctly to user requests. Without accurate intent detection, even advanced conversational systems would struggle to provide meaningful assistance. In addition to understanding intent, conversational AI systems must also identify entities within a user's request. Entities are the specific pieces of information that help complete the user's request. While intent describes what the user wants to do, entities describe important details related to that action. For example, consider the request. I want to book a flight to New York tomorrow. In this sentence, the system would detect several entities. The destination is New York, and the date is tomorrow. These details provide the information needed to complete the task. Entities may include many types of information, such as locations, dates, product names, numbers, or customer identifiers. Extracting entities allows conversational systems to gather all necessary details from user input. Once these details are captured, the system can use them to perform tasks such as booking reservations, retrieving account information, or generating personalized responses. Intent recognition and entity extraction work together to enable conversational systems to understand both the purpose of a request and the details required to fulfill it. AWS provides several services that allow developers to build conversational AI applications efficiently. One of the most important services is Amazon Lex, which allows developers to build chatbots and voice interfaces using natural language understanding. Lex handles intent detection, dialogue management, and integration with other AWS services. Another key service is Amazon Polly, which converts text into natural-sounding speech. This allows conversational systems to communicate with users through voice responses. AWS also provides Amazon Transcribe, which converts spoken language into text. This enables voice-based systems to understand spoken user input. In addition, developers can use Amazon Bedrock to access foundation models that support advanced conversational capabilities, including generative AI responses. By combining these services, developers can create intelligent conversational systems capable of understanding voice input, processing natural language, and generating helpful responses. These tools allow organizations to deploy scalable conversational systems without needing to build complex machine learning models from scratch. Conversational AI is widely used across industries because it improves customer experiences while reducing operational costs. One common application is customer support automation. Chatbots can answer common questions, guide users through troubleshooting steps, and assist with account-related inquiries. In the banking sector, conversational systems help customers check account balances, review transactions, and perform simple banking operations. Healthcare organizations use conversational AI to schedule appointments, provide patient information, and assist with symptom assessment. In e-commerce, conversational assistants help customers discover products, compare features, and complete purchases. Conversational AI is also used internally within organizations to help employees access company knowledge, automate workflows, and retrieve information quickly. Because these systems operate continuously and can handle large numbers of conversations simultaneously, they significantly improve service efficiency. In this lesson, we explored the fundamentals of conversational AI systems and how machines interact with humans through natural language. We began by discussing chatbots, which simulate conversations with users across messaging platforms, websites, and voice interfaces. We then examined conversational design, which focuses on creating interactions that are clear, helpful, and natural for users. Next, we explored intent recognition and entity extraction. Intent recognition identifies what the user wants to accomplish, while entities capture the specific details needed to complete the request. Finally, we looked at AWS tools that enable developers to build conversational AI systems, including services for chatbot development, speech recognition, and speech synthesis. Together, these technologies allow organizations to automate interactions, improve customer experiences, and deliver intelligent digital assistants. In the next lesson, we will explore responsible AI and AI governance, including how organizations ensure that AI systems are developed and used in ethical and responsible ways. An AI data pipeline is a structured workflow that collects, processes, and delivers data to machine learning models and production systems. These pipelines consist of several stages that transform raw data into useful insights. The first stage involves data sources, where raw information originates. Data may come from databases, application programming interfaces, IoT devices, or application logs. The second stage is data processing, where the raw data is cleaned, transformed, and enriched. This step ensures that the data is consistent and suitable for machine learning systems. Next comes the machine learning stage, where models analyze the prepared data and generate predictions or classifications. Finally, the results are delivered to applications where users or automated systems can act on the generated insights. This structured workflow ensures that data moves efficiently through the system. Without a pipeline, it would be extremely difficult to manage the complex flow of data required by modern AI systems. Efficient data pipelines are therefore essential for building scalable and reliable machine learning applications. Machine learning models depend heavily on the quality of the data they receive. In fact, it is often said that models are only as good as the data used to train and operate them. Without proper pipelines, several problems can arise. One issue is inconsistent data. Data may come from multiple sources with different formats or schemas. If these inconsistencies are not resolved, machine learning models may receive corrupted or incomplete inputs. Another issue is stale data. If data pipelines do not update information regularly, models may rely on outdated data. This can cause predictions to become inaccurate over time. A third challenge is unreliable outputs. Poor quality input data often leads to incorrect model predictions, which can negatively impact applications that depend on those predictions. These problems illustrate why well-designed pipelines are critical for machine learning systems. A reliable data pipeline ensures that data is continuously collected, validated, and transformed before being used by AI models. By maintaining consistent and high-quality data flows, organizations can ensure that their machine learning systems produce accurate and trustworthy results. AI data pipelines typically consist of several key stages that work together to transform raw data into actionable insights. The first stage is data ingestion, where raw data is collected from multiple sources. These sources may include databases, APIs, IoT devices, or application logs. The second stage is data storage, where collected data is stored in scalable systems such as cloud storage platforms. This stage ensures that data sets are preserved and accessible for processing. Next comes data processing, where raw data is cleaned, validated, and transformed into formats suitable for machine learning models. Once the data is prepared, it enters the inference stage, where trained machine learning models generate predictions or classifications. Finally, these predictions are delivered to applications or analytic systems where they can be used to support decision-making. Each stage in this pipeline ensures that data is prepared and delivered correctly so that AI systems can operate efficiently and reliably. The first stage of any AI data pipeline is data ingestion, which involves collecting and centralizing data from multiple sources. Data ingestion acts as the entry point for the entire pipeline. It gathers raw data and brings it into a centralized system where it can be processed and analyzed. Data can originate from many different sources. Common examples include traditional databases, external APIs, IoT devices, application logs, and user-generated content. Because these sources often produce data in different formats, ingestion systems must be capable of handling heterogeneous data streams. In modern cloud architectures, ingestion pipelines often support both batch processing and real-time streaming. Batch ingestion collects large datasets periodically, such as daily or hourly updates. Streaming ingestion processes data continuously as it is generated. Cloud platforms provide scalable services that make it possible to ingest massive volumes of data efficiently. Once data has been ingested into the system, it can move to the next stages of the pipeline, where it is processed, transformed, and ultimately used by machine learning models. Effective data ingestion ensures that AI systems receive the information they need to generate accurate predictions and insights. Once we understand the importance of data ingestion, the next step is to explore how AWS supports this process. AWS provides several managed services that allow organizations to ingest data from many different sources at scale. These services support both streaming data ingestion and batch ingestion, depending on the needs of the application. One important service is Amazon Kinesis, which allows organizations to ingest and process streaming data in real time. Kinesis is commonly used for applications that require continuous data streams, such as IoT sensors, clickstream analytics, or real-time monitoring systems. Another key service is AWS Glue, which provides serverless data integration and ETL capabilities. Glue helps organizations extract data from multiple sources, transform it into consistent formats, and load it into storage systems or data warehouses. Amazon S3 also plays a central role in data ingestion pipelines. S3 serves as a scalable storage system where raw data can be stored before processing. Because S3 can handle massive amounts of data, it is often used as the foundation of data lakes. Another useful service is AWS Lambda, which supports event-driven data ingestion. Lambda functions can automatically trigger when new data arrives, allowing pipelines to process data immediately without manual intervention. Together, these services allow organizations to build flexible and scalable ingestion pipelines that collect data efficiently from multiple sources. After data has been ingested and processed, it enters the next stage of the AI pipeline known as model inference. Inference pipelines are responsible for delivering data to trained machine learning models so that predictions can be generated. The inference process typically follows several steps. First, the system receives input data, which has already been cleaned and prepared during earlier pipeline stages. Next, the system sends this input data to a trained machine learning model. The model processes the input using patterns it learned during training. The model then generates predictions or outputs. These outputs may include classifications, recommendations, probability scores, or other forms of insight. Finally, the results are delivered to applications or downstream services. These applications may display results to users, trigger automated actions, or feed the predictions into analytics dashboards. Inference pipelines allow AI systems to move from experimentation into real-world applications. They ensure that machine learning models can continuously receive new data and generate useful insights. Inference pipelines generally operate in two main modes: real-time inference and batch inference. Real-time inference generates predictions immediately when a request is received. This approach is used when applications require instant responses. Examples of real-time inference include chatbots, recommendation systems, fraud detection systems, and voice assistants. In these scenarios, the system must produce predictions within milliseconds or seconds. Batch inference works differently. Instead of processing individual requests immediately, batch inference processes large data sets at scheduled intervals. For example, an organization might run a batch inference job overnight to score millions of customer records. The predictions can then be used for analytics, marketing campaigns, or reporting. Both approaches have advantages depending on the use case. Real-time inference is ideal when responsiveness is critical, while batch inference is better suited for large-scale data processing tasks. Choosing the appropriate inference strategy helps organizations balance performance, scalability, and cost. Another important concept in modern AI infrastructure is serverless architecture. Serverless AI allows developers to build and run machine learning systems without managing servers or infrastructure. In a traditional architecture, engineers must provision servers, manage scaling, and maintain infrastructure. Serverless platforms eliminate much of this operational complexity. One key advantage of serverless architecture is automatic scaling. Resources automatically adjust based on workload demand, ensuring that systems remain responsive even during traffic spikes. Another advantage is event-driven processing. Instead of continuously polling for data, serverless systems respond automatically when new events occur. Serverless systems also use a pay-per-use model, meaning organizations only pay for the compute resources they actually use. These characteristics make serverless architecture particularly attractive for AI pipelines that process unpredictable or bursty workloads. AWS provides several services that make it possible to build fully serverless AI pipelines. One key service is AWS Lambda, which allows developers to run code in response to events without provisioning servers. Lambda can trigger processing steps whenever new data arrives. Amazon API Gateway allows organizations to expose machine learning models as secure and scalable APIs. Applications can send requests to these APIs and receive predictions in real time. Amazon SageMaker provides fully managed infrastructure for training, tuning, and deploying machine learning models. SageMaker simplifies the process of building and operating AI systems at scale. Amazon S3 acts as the central storage layer for many AI pipelines. It stores raw datasets, processed features, and model artifacts. When combined, these services allow developers to create scalable pipelines that automatically process data, run models, and deliver predictions without managing infrastructure. In this lesson, we explored how AI data pipelines connect raw data to intelligent applications. We began by discussing the role of data pipelines in machine learning systems. These pipelines ensure that data flows from its original sources to models and applications in a structured and reliable way. We then explored data ingestion, which collects and centralizes data from sources such as databases, APIs, IoT devices, and application logs. Next, we examined model inference pipelines, which deliver processed data to machine learning models so they can generate predictions and insights. We also compared real-time inference and batch inference, two different strategies for generating predictions depending on application requirements. Finally, we discussed serverless AI architectures, which allow organizations to build scalable AI systems without managing infrastructure. Together, these concepts form the foundation of modern AI infrastructure. In the next lesson, we will explore AI security, governance, and responsible AI, focusing on how organizations ensure that AI systems are deployed safely, ethically, and responsibly. Artificial intelligence is increasingly used to support decisions that affect people's lives. Because of this, responsible AI practices are essential. AI systems now influence decisions in areas such as hiring, credit approvals, healthcare recommendations, and law enforcement operations. For example, in hiring processes, organizations may use AI systems to screen resumes and rank job candidates. If the training data used for these models contains historical biases, the system may unfairly favor certain candidates while disadvantaging others. Similarly, AI systems are used in financial services to evaluate loan applications and determine credit approvals. These systems must be carefully designed to ensure they do not unintentionally discriminate against specific populations. Healthcare is another area where AI is becoming increasingly important. AI models can assist with diagnoses and treatment recommendations, but inaccurate or biased predictions could have serious consequences. Law enforcement agencies sometimes use predictive analytics tools to assess risk or allocate resources. These systems must be designed responsibly to avoid reinforcing historical inequalities. These examples illustrate why responsible AI practices are critical. When AI systems influence high-stakes decisions, organizations must ensure that the models are accurate, fair, and transparent. By implementing responsible AI frameworks, organizations can reduce risks and ensure that AI technologies are used in ways that benefit society. One of the most important challenges in responsible AI is bias. AI bias occurs when a machine learning model produces outcomes that systematically favor or disadvantage certain groups of people. Bias often originates in the training data used to build machine learning models. If historical datasets contain patterns of inequality or discrimination, models trained on that data may learn and reproduce those patterns. Another common cause of bias is incomplete datasets. If certain groups are underrepresented in the training data, the model may not perform accurately for those populations. Bias can also arise from model design choices. For example, objective functions or evaluation metrics that prioritize accuracy alone may overlook fairness considerations. Because machine learning models learn patterns from data, any bias present in the data can become embedded within the model. If these issues are not identified and addressed during development, biased models may produce unfair outcomes when deployed in real-world applications. For this reason, detecting and mitigating bias is a critical step in responsible AI development. Bias can enter AI systems at multiple stages of the machine learning lifecycle. One common source of bias is data collection. If data is gathered from limited sources or does not adequately represent diverse populations, the resulting dataset may be incomplete. Another source of bias occurs during dataset creation. If certain groups are underrepresented in the dataset, models may learn patterns that work well for some populations, but poorly for others. Labeling errors can also introduce bias. When datasets require human annotation, subjective judgments may influence how examples are labeled. Another challenge is imbalanced datasets, where some groups appear far more frequently than others. Models trained on imbalanced data may naturally favor the dominant group. These issues illustrate why careful dataset design is critical. Bias introduced early in the development process can become amplified as the model learns from the data. Detecting bias during data collection and pre-processing helps prevent unfair outcomes from appearing in deployed AI systems. Fairness is one of the central goals of responsible AI. A fair AI system ensures that its predictions and decisions treat individuals and groups equitably. This means that protected characteristics such as gender, race, or ethnicity should not lead to discriminatory outcomes. One important aspect of fairness is avoiding discrimination. AI systems should not produce outcomes that disproportionately disadvantage specific populations. Another key principle is consistency. Similar inputs should produce similar outcomes regardless of demographic characteristics. Achieving fairness requires careful evaluation during model development and testing. Developers must assess how the model performs across different groups and identify any disparities in outcomes. Fairness metrics and evaluation techniques can help identify whether certain populations are being treated differently by the model. If disparities are detected, developers may need to adjust training data, modify model architecture, or apply fairness constraints during training. Ensuring fairness is an ongoing process. AI systems must be continuously monitored after deployment to ensure that they maintain equitable performance as data and conditions evolve. By prioritizing fairness, organizations can build AI systems that support ethical decision-making and promote trust in artificial intelligence technologies. Another important aspect of responsible AI is model safety. Model safety focuses on ensuring that AI systems behave reliably and predictably in real-world environments. Machine learning models are often trained in controlled environments using curated datasets. However, once these models are deployed into real applications, they may encounter unexpected inputs or edge cases that were not present during training. One risk is harmful outputs. In some situations, models may generate offensive, misleading, or dangerous responses if they are not carefully monitored and tested. Another concern is unexpected behavior. A model might behave correctly under normal conditions, but produce incorrect results when faced with unusual inputs or rare scenarios. There are also adversarial attacks, where attackers intentionally design inputs that trick machine learning models into making incorrect predictions. For example, a small modification to an image could cause a computer vision system to misclassify an object. Similarly, carefully crafted text inputs may cause language models to produce unintended responses. Finally, AI systems may be misused in contexts for which they were not designed. For instance, a model built for recommendation systems should not be applied to high-risk decisions without proper validation. To address these risks, organizations must implement strong testing procedures, monitor model behavior in production, and design safeguards that prevent harmful outputs. Ensuring model safety is critical for building AI systems that users can trust. AI systems also introduce new types of security risks that organizations must address. One major threat is data poisoning. In this type of attack, malicious actors intentionally manipulate the training data used to build a model. If the corrupted data is not detected, the model may learn incorrect patterns and produce misleading predictions. Another risk is model theft. Attackers may attempt to extract proprietary models by repeatedly querying an AI system's API and analyzing the responses. Over time, they may be able to recreate a similar model. AI systems are also vulnerable to adversarial inputs. These are specially crafted inputs designed to fool machine learning models into making incorrect predictions. For example, slight modifications to images may cause computer vision systems to misidentify objects. Another concern is unauthorized access. If AI systems are deployed through APIs or cloud services, attackers may attempt to access model endpoints without permission. Because AI systems rely heavily on data and model infrastructure, protecting these components is essential. Organizations must implement security controls such as authentication, encryption, monitoring, and access restrictions to safeguard their AI systems. To ensure responsible use of artificial intelligence, organizations must establish AI governance frameworks. AI governance refers to the policies, processes, and oversight mechanisms that guide how AI systems are developed, deployed, and monitored. One key aspect of governance is model documentation. Teams must document how models are trained, what datasets are used, and how predictions are generated. This creates transparency and allows organizations to track model behavior over time. Another important practice is risk assessment. Before deploying an AI system, organizations should evaluate potential risks and determine whether the model may have unintended consequences. Governance frameworks also include compliance monitoring. Organizations must ensure that AI systems comply with legal regulations and industry standards. Finally, governance involves ethical review processes, where human oversight ensures that AI systems are aligned with ethical principles and societal values. Effective governance ensures that AI systems remain accountable, transparent, and compliant throughout their lifecycle. Responsible AI is not a one-time activity. Instead, it requires continuous oversight and improvement throughout the lifecycle of an AI system. One important practice is auditing training datasets. Developers should evaluate datasets for bias, missing data, and representation gaps before training models. Another practice is evaluating model fairness. Models should be tested across different demographic groups to ensure that outcomes remain equitable. Organizations should also monitor model performance after deployment. Over time, data patterns may change, which can cause models to drift and produce inaccurate predictions. Continuous monitoring helps detect these issues early. Transparency is another important principle. Teams should document how models work and how decisions are made so that stakeholders can understand and evaluate AI systems. By combining these practices, organizations can maintain responsible and trustworthy AI systems throughout their life cycle. In this lesson, we explored the principles of responsible AI and security in artificial intelligence systems. We began by examining AI bias, which occurs when models produce unfair outcomes for certain groups due to biased data or flawed design. We then discussed fairness, which ensures that AI systems treat individuals and groups equitably. Next, we explored model safety, which focuses on ensuring that AI systems behave reliably and avoid harmful outputs or unintended consequences. We also examined security risks in AI systems, including data poisoning, model theft, adversarial attacks, and unauthorized access. Finally, we discussed AI governance, which provides the policies and oversight needed to ensure that AI systems are developed and deployed responsibly. Together, these principles help organizations build AI systems that are safe, ethical, and trustworthy. In the next lesson, we will focus on AI certification review and practice exam preparation, where we will review the key concepts covered in this course and prepare for the AWS AI Practitioner certification exam. To understand AI architecture patterns, we must first examine the core components that make up modern AI systems. As illustrated in the slide deck, AI systems consist of multiple interconnected layers that work together to deliver intelligent functionality. The first component is data pipelines. Data pipelines are responsible for collecting, ingesting, transforming, and routing raw data into machine learning workflows. Data can come from many sources, including databases, applications, sensors, or streaming systems. The second key component is the machine learning model itself. Models are trained using data and generate predictions, classifications, or insights based on patterns learned during training. Once a model is trained, it must be made available to other systems through APIs and services. APIs allow applications to send input data to a model and receive predictions in return. Next, we have application interfaces, which deliver AI-powered functionality to end users. These interfaces may be mobile apps, web platforms, or enterprise systems that integrate AI capabilities into everyday workflows. Finally, modern AI systems require monitoring and observability tools. Monitoring systems track model performance, system health, and data drift. This ensures that models continue to perform correctly once they are deployed in production. Together, these components form the foundation of modern AI architectures. Understanding how these components interact is essential for designing scalable and reliable AI systems. One of the most important architecture patterns used in modern AI systems is serverless AI architecture. Serverless architecture allows developers to run AI workloads without managing servers or infrastructure. Instead of provisioning and maintaining servers, developers simply deploy code and models while the cloud platform handles scaling and resource management. According to the slide deck, serverless AI architecture has several defining characteristics. First, it supports automatic scaling. Resources scale up or down based on demand without requiring manual intervention. For example, if a large number of users request predictions from a model, the system automatically allocates additional compute resources. Second, Serverless systems are event-driven. This means execution is triggered by events such as API requests, data uploads, or scheduled tasks. Third, serverless architectures have low operational overhead. Developers do not need to manage operating systems, patch servers, or plan infrastructure capacity. Instead, they can focus entirely on building AI applications and improving model performance. This architecture pattern is especially useful for organizations that want to deploy AI applications quickly while minimizing infrastructure complexity. Serverless AI allows teams to concentrate on delivering value rather than managing infrastructure. Serverless AI architectures offer several important benefits that make them attractive for modern AI applications. One of the most significant advantages is automatic scaling. Serverless platforms automatically allocate computing resources based on workload demand. This means applications can handle traffic spikes without requiring manual infrastructure planning. Another important benefit is cost efficiency. Serverless platforms typically follow a pay-per-use pricing model, meaning organizations only pay for the compute resources that are actually used. When the system is idle, there are no unnecessary infrastructure costs. Serverless architectures also simplify deployment and development workflows. Developers can deploy models and application logic without worrying about managing servers, configuring operating systems, or maintaining runtime environments. This reduces operational complexity and accelerates development cycles. As highlighted in the slide visuals, these benefits allow teams to ship AI features faster and focus on innovation instead of infrastructure management. By reducing operational overhead and improving scalability, serverless architectures enable organizations to build and deploy AI applications more efficiently. Cloud platforms such as AWS provide a rich ecosystem of services that enable serverless AI architectures. These services allow developers to build complete AI pipelines without managing infrastructure. One of the key services used in serverless AI systems is AWS Lambda. Lambda allows developers to run code in response to events without provisioning or managing servers. This makes it ideal for running model inference functions triggered by API requests or data uploads. Another important component is Amazon API Gateway. API Gateway allows developers to expose machine learning models as secure and scalable APIs. Applications can send requests to the API and receive predictions from the model in real time. For machine learning development and deployment, AWS provides Amazon SageMaker. SageMaker offers managed capabilities for training, tuning, and deploying machine learning models. It simplifies the entire machine learning lifecycle. Finally, Amazon S3 provides highly durable storage for datasets, training artifacts, and model outputs. Together, these services form a powerful serverless architecture that supports scalable and reliable AI systems. By combining storage, compute, APIs, and machine learning services, organizations can build fully managed AI pipelines that automatically scale to meet demand. As AI systems move from experimentation to real-world deployment, scalability becomes one of the most important architectural requirements. A scalable AI system is designed to handle increasing workloads without sacrificing performance, reliability, or responsiveness. In production environments, AI systems must often process massive amounts of data while serving predictions to large numbers of users simultaneously. Modern AI platforms may need to handle billions of data points, thousands of model inference requests per second, and continuous streams of incoming data. To support these demands, scalable AI architectures rely on cloud infrastructure and distributed computing systems. Instead of running on a single server, workloads are distributed across multiple computing resources that work together to process tasks efficiently. Another important aspect of scalable systems is high availability. Production AI systems must maintain uptime even during infrastructure failures or unexpected traffic spikes. Many organizations aim for reliability targets such as 99.9% uptime or higher. Automation also plays a critical role in scalability. Ideally, systems should scale automatically based on demand rather than requiring manual intervention from engineers. This means infrastructure should dynamically allocate additional resources when workloads increase and release them when demand decreases. Scalable architectures also make it easier for organizations to expand AI capabilities over time. As datasets grow and new features are added, the system can evolve without requiring major redesigns. By designing AI systems with scalability in mind, organizations ensure that their applications remain reliable, efficient, and capable of supporting future growth. To achieve scalability in AI systems, organizations use several architectural strategies that allow systems to handle increasing workloads efficiently. One common strategy is distributed data processing. Large datasets can be split across multiple computing nodes so that each node processes a portion of the data simultaneously. This approach dramatically improves processing speed and allows systems to handle very large datasets. Another important strategy is model replication. Instead of running a single instance of a machine learning model, multiple identical model instances can run in parallel. When prediction requests arrive, they are distributed across these instances. This improves both system performance and availability. A third strategy is load balancing. Load balancers distribute incoming requests evenly across multiple servers or model instances. This prevents any single component from becoming overloaded and ensures that traffic is handled efficiently. Finally, organizations rely on cloud infrastructure to provide elastic resources. Cloud platforms allow computing resources such as CPUs, GPUs, memory, and storage to scale automatically based on demand. These scaling strategies work together to create AI systems that remain fast, reliable, and resilient even as workloads grow significantly. By combining distributed processing, replication, load balancing, and cloud infrastructure, organizations can design AI systems capable of supporting large-scale production environments. Another important architecture pattern in modern AI systems is event-driven machine learning. Event-driven architectures allow systems to automatically respond to new data or user actions in real time. Instead of continuously checking for new data through polling, the system reacts immediately when an event occurs. For example, an event could be triggered when a new file is uploaded to a storage system, a user submits a request through an application, a sensor generates new data, a transaction occurs in a system. When the event occurs, it triggers an automated workflow that processes the data and may invoke a machine learning model to generate predictions. This architecture significantly reduces latency because the system does not need to wait for scheduled processing cycles. Event-driven machine learning is especially useful in applications that require real-time responses, such as fraud detection, recommendation systems, anomaly detection, and automated alerts. For example, when a financial transaction occurs, an event-driven system can immediately trigger a fraud detection model. The model evaluates the transaction and determines whether it appears suspicious. Similarly, in recommendation systems, user activity can trigger real-time updates to personalize suggestions. Event-driven architectures allow AI systems to operate continuously and respond to changing data instantly. This capability is critical for modern applications where users expect immediate responses and real-time insights. Cloud platforms provide powerful tools for building event-driven AI systems, and AWS offers several services that enable these architectures. One of the core components is AWS Lambda. Lambda is a serverless compute service that automatically runs code in response to events. For example, when new data is uploaded or an API request is received, Lambda functions can execute model inference logic. Another important service is Amazon Event Bridge. Event Bridge allows organizations to route events between different services using rule-based logic. It acts as a central event bus that coordinates communication between applications, services, and workflows. Storage systems can also generate events. For example, Amazon S3 can trigger events whenever a new file is uploaded or modified. This allows AI workflows to automatically process new datasets as soon as they become available. For high-volume streaming data, AWS provides Amazon Kinesis. Kinesis supports real-time ingestion and processing of large data streams. AI models can consume this streaming data to generate insights or predictions continuously. By combining these services, organizations can build fully automated pipelines where AI models respond instantly to new data. This architecture enables scalable, real-time AI systems that operate efficiently without manual intervention. In this lesson, we explored AI architecture patterns that support scalable and production-ready AI systems. First, we introduced the concept of architecture patterns, which serve as structural blueprints for building reliable and maintainable AI applications. We then examined serverless AI architectures, which allow organizations to deploy AI workloads without managing infrastructure. These architectures automatically scale and reduce operational complexity. Next, we discussed scalable AI systems, which are designed to support growing workloads, increasing data volumes, and large numbers of users. We explored several strategies used to achieve scalability, including distributed data processing, model replication, load balancing, and cloud-based infrastructure. These techniques ensure that AI systems remain performant and reliable even as demand increases. Finally, we examined event-driven machine learning architectures, which allow AI systems to respond instantly to data events and user actions. Event-driven workflows enable real-time AI applications such as fraud detection, recommendation systems, and anomaly monitoring. Cloud services like AWS Lambda, EventBridge, Amazon S3, and Kinesis make it possible to build these reactive AI pipelines efficiently. Together, these architecture patterns provide the foundation for modern AI systems deployed in production environments. Understanding these design approaches will help you build AI solutions that are scalable, resilient, and capable of supporting enterprise-scale workloads. In the next lesson, we will move into certification review and practice exam preparation, where we will review key concepts from this course and prepare for the AWS AI Practitioner certification exam. The AWS AI Practitioner exam evaluates your conceptual understanding of artificial intelligence and machine learning technologies, particularly in the context of AWS. One important thing to remember is that this exam focuses on concepts rather than coding skills. You are not expected to write machine learning algorithms or implement complex models. Instead, the exam tests your understanding of how AI systems work and how AWS services support AI applications. The exam focuses on several major topic areas. The first domain is AI and machine learning fundamentals. This includes core concepts such as supervised learning, training data, model evaluation, and the general workflow of machine learning systems. The second domain is generative AI. This includes concepts such as foundation models, large language models, prompt engineering, and generative AI applications. The third domain focuses on AWS AI Services. You should understand how services like SageMaker, Bedrock, Recognition, and Comprehend are used to build AI-powered solutions. You should also understand when to use these services in real-world applications. The final domain is responsible AI. This includes topics such as fairness, bias, governance, and ethical considerations in AI systems. Understanding these domains will prepare you for the majority of questions you will encounter on the exam. Before taking the exam, it is important to understand the types of questions you will encounter. AWS certification exams typically include 3 types of questions. The first type is multiple choice questions, where you select the single best answer from several options. These questions test your understanding of core concepts and AWS services. The second type is multiple response questions. In these questions, you must select all answers that are correct. This means there may be more than one correct option. These questions can be more challenging because selecting only some of the correct answers may result in an incorrect response. The third type is scenario-based questions. These questions present a real-world scenario and ask you to determine the best solution using AWS technologies. For example, you may be given a description of a company building a machine learning pipeline and asked which AWS services should be used. These scenario-based questions often test your understanding of architecture patterns and service selection. Another important factor during the exam is time management. You must pace yourself carefully so that you have enough time to review questions before submitting your answers. Understanding the question format ahead of time helps reduce stress and allows you to focus on selecting the correct answers. To succeed in the AWS AI Practitioner exam, it is important to understand the key knowledge domains that the exam evaluates. The exam focuses on several major domains that represent the core skills required for working with AI on AWS. The first domain is AI fundamentals. This includes basic AI terminology, machine learning concepts, and the overall workflow of building and deploying AI models. You should understand how models are trained, how data is prepared, and how predictions are generated. The second domain is machine learning workflows. This includes the process of preparing datasets, training models, evaluating performance, and deploying models for inference. The third domain is generative AI concepts. You should understand foundation models, large language models, prompt engineering techniques, and common generative AI use cases. The fourth domain is AWS AI Services and architecture. This includes services such as SageMaker, Bedrock, Recognition, and other AWS AI tools used for building AI applications. The final domain is responsible AI and governance. You should understand concepts such as bias, fairness, transparency, and ethical considerations in AI systems. Mastering these domains ensures that you have a well-rounded understanding of AI systems and AWS AI technologies. Now that we understand what the exam tests, let's discuss a practical strategy for answering questions effectively. A structured approach can significantly improve your accuracy during the exam. The first step is to read the question carefully. Look for important keywords such as serverless, most cost-effective, managed service, or real-time processing. These keywords often indicate which AWS service is the correct choice. The second step is to eliminate clearly incorrect answers. Many exam questions include distractor options that are technically possible but not the best solution. Removing these options makes it easier to identify the correct answer. The third step is to compare the remaining choices carefully. AWS often expects the most efficient and cloud-native solution. For example, managed services are usually preferred over manually configured infrastructure. Finally, once you have selected your answer, confirm it and move on to the next question. Spending too much time on a single question can reduce the time available for the rest of the exam. Following this structured strategy helps reduce confusion and improves accuracy across the entire exam. One of the most important skills during the certification exam is time management. Many candidates know the material, but struggle because they spend too much time on a small number of questions. The goal during the exam is not perfection on every question. Instead, the goal is to make steady progress and maximize your total score. A good strategy is to answer the easier questions first. When you encounter a question that you immediately understand, answer it quickly and move forward. This builds momentum and ensures that you secure points early in the exam. When you encounter a difficult question, do not spend excessive time trying to solve it immediately. Instead, flag the question and return to it later. Most exam platforms allow you to mark questions for review. This approach helps you avoid getting stuck and allows you to focus on questions where you are more confident. Another important rule is to remember that no single question is worth sacrificing too much time. If you spend several minutes struggling with a single problem, you may lose valuable time that could be used to answer several easier questions. Maintaining a steady pace throughout the exam ensures that you have enough time to review your answers before submitting. By managing your time effectively, you increase your chances of completing the exam calmly and confidently. Even well-prepared candidates sometimes lose points due to common exam traps. These traps are designed to test whether you truly understand AWS services and architecture patterns. One common mistake is missing important keywords in the question. Words such as most cost-effective, serverless, fully managed, or scalable often indicate the direction AWS expects you to choose. Ignoring these keywords can lead you to select an answer that technically works but is not the best solution. Another common trap is confusing similar AWS services. For example, candidates may mix up services like SageMaker, Bedrock, Recognition, or Comprehend if they do not clearly understand their primary use cases. It is important to remember what each service is designed to do. Another mistake is ignoring cost efficiency. AWS architecture questions often emphasize solutions that are both effective and cost efficient. The correct answer is usually the one that balances performance, scalability, and cost. Finally, candidates sometimes select an answer that is technically correct, but not optimal. AWS exams often ask for the best solution, not simply a solution that could work. Being aware of these traps helps you avoid unnecessary mistakes. Architecture-based questions are a major part of the AWS certification exam. These questions present real-world scenarios and ask you to choose the best architecture using AWS services. For example, you may be given a scenario where a company needs to deploy a machine learning model for real-time predictions. In this situation, you may need to identify services such as SageMaker endpoints for model deployment or serverless architectures that allow models to scale automatically. Another common scenario involves event-driven pipelines. In these architectures, services such as AWS Lambda, SNS, or SQS trigger machine learning workflows whenever new data arrives. For example, when a new file is uploaded to cloud storage, an event may trigger a function that processes the data and runs model inference. Architecture questions may also focus on serverless AI systems. These systems rely on managed cloud services that automatically scale without requiring infrastructure management. In these questions, AWS typically expects the answer that uses managed services instead of manually configured infrastructure. Understanding architecture patterns such as serverless design, event-driven processing, and scalable AI pipelines will help you answer these questions confidently. Practice questions are one of the most effective ways to prepare for the certification exam. However, practicing effectively requires more than simply memorizing answers. The most important step is to understand why an answer is correct. Instead of focusing only on getting the correct answer, take time to analyze the reasoning behind the solution. This helps reinforce your understanding of AWS services and architecture patterns. Another useful strategy is to carefully review incorrect answer choices. Wrong answers often reveal common misconceptions or misunderstandings about AWS services. By studying these incorrect options, you learn to recognize and avoid similar mistakes during the real exam. Practice questions also help you identify patterns in AWS architecture design. Many AWS solutions follow predictable design approaches, such as using managed services, serverless architectures, and scalable cloud infrastructure. By recognizing these patterns, you will be able to answer scenario-based questions more quickly. Consistent practice builds both knowledge and confidence. Over time, you will become more comfortable interpreting exam questions and identifying the correct solutions. As you approach the certification exam, it is helpful to review several key preparation steps. First, revisit the core AWS AI services covered in this course. You should feel comfortable identifying when to use services such as SageMaker, Bedrock, Recognition, and Comprehend. Second, review the architecture patterns that appear frequently in exam questions. These include serverless AI architectures, event-driven pipelines, and scalable machine learning systems. Understanding these patterns will help you evaluate scenario-based questions more effectively. Third, continue practicing with scenario-based questions under timed conditions. Simulating exam conditions helps improve your time management and decision-making skills. Finally, approach the exam with confidence. If you have completed the lessons in this course and practiced reviewing AWS AI concepts, you already have the knowledge needed to succeed. Certification exams are designed to test your understanding of core principles rather than obscure details. Stay calm, read questions carefully, apply the strategies you have learned, and trust your preparation. At this point, you are ready to attempt the AWS AI Practitioner Certification exam and demonstrate your knowledge of AI systems on AWS.